Look up tonight, and you will see a sky full of distant fires. Every point of light beyond our own solar system is either a star inside our galaxy or, if you know where to look, the smudged glow of an entire other galaxy. A city of hundreds of billions of suns, so far away that its light left home before the pyramids were built, before language was written, sometimes before humans existed at all. That sky will not last forever. Not because the stars will burn out, although they will. Not because something will destroy the galaxies, although in a sense, something already is. The sky will not last because the universe itself is quietly pulling the curtain closed, one galaxy at a time. And it has been doing this since long before anyone was here to notice. Here is the strange part. The ending will not happen all at once, and it will not happen because galaxies fly apart or burn up or collide into oblivion. Most of them will simply leave. They will cross a boundary that cannot be seen, cannot be touched, and cannot be stopped. And once they cross it, no signal, no light, no radio wave, no gravitational ripple will ever be able to follow them back. They will still exist. We simply will never be able to know that again. Tonight, we are going to ask a question that sounds like science fiction, but is, in fact, one of the most carefully studied predictions in modern cosmology. What will the universe actually look like after every galaxy beyond our own has vanished from view? To answer it properly, we cannot start with the ending. We have to start why galaxies are visible at all, and why that visibility is a temporary gift, not a permanent feature of reality. Astronomers already have a name for the era we are living in. They call it the stelliferous era, the age of starlight. It began roughly a few 100 million years after the Big Bang, when the first stars switched on, and it is still going. We are deep inside it right now, in a universe still rich with galaxies, still busy forming new stars, still young enough, cosmologically speaking, that the night sky is full. But the stelliferous era has a closing date, not a dramatic one, a quiet one, and the mechanism that ends it is the same mechanism that, eventually, will erase galaxies from each other's view entirely. The expansion of space itself. By the end of this documentary, you will understand why that expansion, which today is gentle enough that it barely registers, even to precision instruments, will eventually become the single most powerful force in the cosmos. You will understand why nearly every galaxy you can currently see is, in the most literal sense, a ghost. Light that left billions of years ago, showing you a place that may no longer exist in the form you're seeing it. And you will understand why a small number of galaxies, including our own neighbors, are actually exempt from this fate, bound together by gravity, strongly enough to resist the pull of an expanding universe, destined to merge into a single, lonely island of light, long after everything else has faded from view. To understand how that happens, we need to start with something much closer to home. The difference between a galaxy moving away from us and space itself growing between us. When most people picture galaxies receding from each other, they imagine something like cars driving apart on a highway. Objects in space, moving through space, getting farther apart because they have velocity. That picture is wrong, and the correction matters enormously for everything that follows. Galaxies are not, for the most part, flying away from each other through space. Space itself is expanding, and the galaxies are essentially stationary passengers riding along on a fabric that is stretching. Imagine two ants standing on the surface of a balloon. Neither ant is walking, but as the balloon inflates, The distance between the ants grows anyway, because the rubber between them is stretching. From the perspective of either ant, the other one appears to be retreating, but neither one is actually moving across the surface. That is the cosmos. The surface is space itself, and it has been stretching since the Big Bang, roughly 13.8 billion years ago. This distinction is not a minor technicality. It explains something that would otherwise be deeply strange. Galaxies that are far enough away from us appear to be receding faster than the speed of light. If galaxies were physical objects moving through static space, this would violate Einstein's relativity, which forbids anything from exceeding light speed. But because it is the space between us that is expanding, not the galaxies moving through it, no law of physics is broken. Nothing is traveling faster than light. The distance between 2 points is simply growing, and over large enough distances, that growth rate can exceed the speed of light. Edwin Hubble first noticed the telltale sign of this expansion in the 1920s, when he discovered that distant galaxies are systematically redshifted. Their light stretch toward longer, redder wavelengths in proportion to their distance. The farther away a galaxy is, the more its light has been stretched, and the faster it appears to be receding. This relationship became known as Hubble's law, and the number that describes how quickly space is stretching is called the Hubble constant. Currently estimated at somewhere around 10⁻⁷ kilometers per second for every megaparsec of distance, with astronomers still working to narrow down the exact figure through several independent and slightly disagreeing methods. What that number means in practice is this: for every additional 3.26 million light-years of distance between us and another galaxy, that galaxy appears to be receding about 67 to 73 kilometers per second faster than the last one. It sounds small. It is not small. Multiply that rate across billions of light-years, and the recession velocities become staggering, eventually exceeding the speed of light itself. Not because anything is moving that fast, but because there is simply so much space being created between here and there. Here is where the documentary's central mystery begins to take shape. If the universe were expanding at a constant rate, gravity would still be fighting back the entire time, slowly breaking the expansion, the way a ball thrown upward decelerates under Earth's gravity. For most of the 20th century, that's exactly what cosmologists assumed. A universe with enough matter in it to eventually slow expansion down, perhaps even reverse it. In 1998, two independent teams of astronomers observing distant exploding stars called Type Ia supernovae discovered something that did not fit that picture at all. The expansion of the universe is not slowing down. It is speeding up. To understand why an accelerating universe was such a shock, you have to understand what astronomers were actually trying to measure. Type Ia supernovae are sometimes called standard candles because they explode with remarkably consistent brightness. A white dwarf star pulling in matter from a companion until it crosses a critical mass threshold and detonates in a runaway thermonuclear explosion. Because the explosion mechanism is so consistent, astronomers can use the supernova's actual brightness, compared to how bright it appears from Earth, to calculate precisely how far away it is. Two research groups, the Supernova Cosmology Project and the High-Z Supernova Search Team, independently used this technique to measure cosmic expansion at different points in the universe's history. The plan was straightforward: Track the expansion rate at different distances. See how much gravity has been slowing things down, and use that to calculate the universe's overall mass and its likely fate. The data came back wrong. Or rather, it came back correct, and what it revealed was a universe behaving in a way nobody had predicted. Distant supernovae appeared fainter than they should have if the universe were merely coasting or decelerating. That faintness meant the supernovae were farther away than a decelerating universe would put them, which meant the expansion rate, instead of slowing down over cosmic history, has been speeding up. This result earned the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rices. And it forced cosmology to confront an uncomfortable question. What is causing the expansion to accelerate? The leading explanation has a name, but the name is mostly a placeholder for something nobody fully understands. Dark energy. Dark energy is not a substance in the way that matter is a substance. The best current understanding treats it as a kind of energy embedded in the vacuum of space itself, meaning that as space expands and creates more volume, it also creates more of whatever this energy is, which in turn pushes space to expand even faster. It is, in effect, a feedback loop with no obvious break. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. According to the current standard model of cosmology, often called lambda CDM, where lambda represents dark energy and CDM stands for cold dark matter. Dark energy makes up roughly 68% of the total energy density of the universe. Dark matter, the separate and equally mysterious substance responsible for holding galaxies together gravitationally, makes up about 27%. Ordinary matter, every star, planet, and person, makes up roughly 5%. We are, by this accounting, a minority presence in our own universe, vastly outweighed by two forms of energy and matter that we cannot directly see, and one of which seems determined to eventually pull every visible structure apart. It is worth being honest about how little is actually understood about what dark energy is. Beneath the label, several competing theoretical frameworks attempt to explain it, and none has yet achieved a definitive advantage over the others. The simplest explanation, and the one most consistent with current data, treats dark energy as what Einstein originally called the cosmological constant, a fixed energy density built into the very fabric of space, unchanging over time, present in every cubic meter of vacuum, regardless of when or where you measure it. Ironically, Einstein introduced this same concept decades earlier, in 1917, for an entirely different reason. He wanted his equations to describe a static, unchanging universe, and the cosmological constant was the mathematical tool, he added, to balance gravity's pull and prevent the universe from collapsing. When Hubble's observations later revealed the universe was expanding, Einstein reportedly considered the cosmological constant his greatest blunder. Only for cosmologists, decades after his death, to discover that something resembling it was real after all, just playing a very different role than he had originally imagined. A second family of explanations, broadly called quintessence models, propose that dark energy is not a fixed constant but a dynamic field that can change in strength over cosmic time, strengthening, weakening, or even potentially reversing sign at some point in the far future. These models remain viable, specifically because current measurements, while consistent with a constant value, are not yet precise enough to rule out slow changes over billions of years. A third, more exotic category of explanations questions whether dark energy needs to exist as a distinct phenomenon at all, suggesting instead that our equations of gravity might need modification on the largest cosmic scales. Meaning the apparent acceleration could be a signal that general relativity itself breaks down or requires adjustment at extreme distances, rather than evidence for a new form of energy. Most cosmologists consider this less likely than the dark energy explanations, given how well general relativity has performed in every other tested context, but it remains an active area of research, precisely because the fundamental nature of dark energy is still unresolved. For the purposes of this documentary, what matters most is not which specific theoretical model eventually proves correct, but the empirical fact, confirmed by multiple independent lines of evidence, that the expansion of space is accelerating and has been for billions of years. The deeper explanation for why remains one of the most significant open questions in all of physics. A genuine, unresolved mystery sitting at the foundation of everything we are about to explore. This is the hidden engine behind everything in this documentary. Dark energy is patient. It does not destroy galaxies through violence. It does something quieter and, in the long run, far more total. It stretches the space between galaxies until light itself can no longer make the crossing. If dark energy eventually wins everywhere, why won't every galaxy in the universe simply drift apart from every other galaxy individually, leaving each one stranded and alone? The answer lies in a competition that is happening right now, on a scale small enough that we can actually observe it directly. The contest between dark energy's outward push and gravity's inward pull, fought at the scale of galaxy clusters, on very large scales, between galaxy clusters separated by hundreds of millions of light years. Dark energy wins decisively because gravity weakens with distance, while dark energy's effect scales with the volume of space itself. But on smaller scales, where galaxies are close enough for their mutual gravitational attraction to be strong, gravity still dominates completely. Dark energy has essentially no detectable influence on the orbit of the Earth around the Sun, or the structure of the Milky Way, or the gravitational dance between our galaxy and its nearest large neighbors. This is why astronomers distinguish between bound systems and unbound systems. A bound system, like our Milky Way, the Andromeda galaxy, and the roughly 80 other smaller galaxies that together make up what's called the local group, is held together by gravity strongly enough that the expansion of space between its members is essentially irrelevant. These galaxies are not riding the expanding fabric of space the way distant galaxies are. They are gravitationally tethered to each other, the way the Earth and Moon are tethered, despite the universe expanding all around them. An unbound system, essentially every other galaxy cluster beyond our local group, is too far away and too weakly connected gravitationally for that tether to matter. For these galaxies, dark energy's stretching effect outweighs gravity's grip entirely, and they are slowly, permanently receding. This single distinction determines almost everything about the long-term future of the visible sky. The local group will not be pulled apart by expansion. Over the coming billions of years, the Milky Way and Andromeda, already approaching each other at roughly 110 kilometers per second, will merge, likely sometime in the next 4 to 5 billion years, into a single, larger galaxy that astronomers have informally nicknamed Milkomeda. Other smaller members of the local group will likely fall into this merged galaxy as well, over a much longer timescale extending tens of billions of years into the future. Everything else, the Virgo cluster, the galaxy superclusters, the vast cosmic web of filaments and voids that map out the large-scale structure of the universe, will continue to recede from us, not because anything is moving, because the space between here and there is still, every moment, getting larger. This is the moment in our story where the title's premise begins to take its true shape. The universe is not going to lose its galaxies through destruction. It is going to lose them through separation, a slow, gravity-driven sorting process in which everything close enough to be gravitationally bound survives together, while everything farther away drifts beyond the reach of light itself. And beyond the reach of light is not a metaphor. It is a literal, calculable boundary with a name. Every observer in the universe, including us, is surrounded by something that sounds like it belongs in a description of a black hole, but applies just completely to ordinary empty space, an event horizon. In the context of an accelerating universe, this is usually called the cosmological event horizon, and it represents the absolute maximum distance from which light, emitted right now, will ever be able to reach us. No matter how much time passes in the future, this is a genuinely strange concept, so it is worth sitting with it for a moment. Because dark energy causes the expansion rate to increase over time, there exists a distance beyond which space is stretching faster than light can travel through it. Light emitted by a galaxy beyond that distance is not merely delayed. It is, in a meaningful sense, swimming against a current that grows stronger the longer it swims, and a current that, for the most distant galaxies, already exceeds light's own speed. Current estimates place this cosmological event horizon at roughly 16 billion light-years away, although the precise figure depends on the exact values cosmologists use for the universe's expansion rate and dark energy density, numbers still being refined by ongoing observational projects. This horizon is fundamentally different from another distance that gets discussed in cosmology: the observable universe, often cited as roughly 46.5 billion light-years in radius. The observable universe describes how far away the most ancient light we can currently detect actually originated, accounting for the expansion that has occurred during its multi-billion-year journey to us. The cosmological event horizon describes something forward-looking instead. The boundary beyond which light emitted today will never arrive, no matter how patiently we wait. Here is the part that reshapes how we should think about the night sky tonight. Galaxies beyond our cosmological event horizon are not necessarily destroyed, not necessarily gone, not necessarily anything dramatic at all. They almost certainly still exist, going about their long, slow stellar lives exactly as they always have. They have simply crossed into a region of space causally disconnected from us, a place where no signal we send can reach them, and no signal they send can reach us ever again. And the genuinely unsettling part is this: that horizon is not static, because the expansion of the universe continues to accelerate. The cosmological event horizon is slowly, continuously swallowing more of the universe. Galaxies that are currently visible to us, galaxies whose light we can detect today, will, over sufficiently long timescales, cross beyond that horizon. and disappear from our potential view forever, not because they moved, because the boundary moved to include them. This is the actual mechanism behind the title of this documentary. Galaxies will not blink out of existence. They will recede beyond a horizon that grows more inclusive with every passing eon, vanishing not in an instant, but the way a friend's voice fades when they walk far enough away that the sound can no longer reach you. Except, in this case, the walking away never ends, and the distance never stops growing, and eventually no shout, no light, no signal of any kind could ever close that gap again. There is a useful, if imperfect, comparison here to the event horizon of a black hole. And it is worth being precise about both the similarity and the difference, because the comparison is often made carelessly. Black hole's event horizon is a boundary in space, surrounding an extremely concentrated mass, beyond which the curvature of space-time is so extreme that no path through that curved space-time leads back outward, not even for light. Once something crosses that boundary, it is not that escape becomes merely difficult. Every possible direction of travel, in a very real geometric sense, leads further inward. The boundary is fixed in position relative to the black hole itself, shaped entirely by the mass that creates it. A cosmological event horizon is different in origin, but eerily similar in consequence. It is not caused by any concentration of mass-curving spacetime around a single point. It is caused by the uniform stretching of space everywhere, all at once, with the accelerating rate of that stretching creating an effective boundary around every single observer in the universe individually. Every galaxy, every star, every hypothetical observer anywhere in the cosmos has their own personal cosmological event horizon, centered on themselves, just as we have ours. A civilization in a galaxy 10 billion light-years away would have an event horizon of their own, encompassing an entirely different, though partially overlapping, slice of the universe than the one we can ever reach. This is one of the more humbling implications buried inside the mathematics. There is no special, privileged vantage point anywhere in the cosmos from which an observer could see more of the universe than anyone else. Every observer, no matter where they are located, finds themselves at the center of their own horizon, with their own boundary of permanent causal disconnection, slowly swallowing more of the universe around them in every direction, for as long as the accelerating expansion continues. It is worth being precise about what disappearing actually means here, because the process unfolds in stages, not as a single dramatic moment. The first stage is redshift increasing without bound. As a receding galaxy's distance grows, the light it emits gets stretched to longer and longer wavelengths. First from visible light into infrared, then from infrared into microwave and radio wavelengths, continuing to stretch as the galaxy's recession velocity climbs ever closer to and eventually beyond the speed of light relative to us. Eventually, the stretching becomes so extreme that any individual photon's wavelength approaches the size of the observable universe itself, and its energy becomes vanishingly small, in principle still present, but practically undetectable by any conceivable instrument. The second stage is dimming, independent of redshift. A galaxy's apparent brightness decreases as the square of its increasing distance. The same inverse square law that makes a streetlight dimmer the farther you walk from it, combined with the stretching of its light into undetectable wavelengths, a sufficiently distant galaxy doesn't just become fainter, It becomes fainter at an accelerating rate, fading toward invisibility on a timescale of tens of billions of years for galaxies currently near our cosmological horizon. The third stage, and the truly final one, is the crossing of the event horizon itself. Once a galaxy's recession velocity, driven by the ever-increasing expansion of space between it and us, permanently exceeds the speed of light, any photon it emits from that moment onward will never close the gap. It isn't that the photon slows down or loses energy completely. It's that the space it must travel through is being created faster than the photon can cross it. The photon is, in effect, running on a treadmill that is accelerating away beneath its feet faster than it can run. Crucially, light already emitted before that crossing, light that is already partway through its multi-billion-year journey toward us, will still eventually arrive, redshifted and dim, but real. This means that even after a distant galaxy crosses beyond the point where its future light could ever reach us, we will continue receiving its older light for a very long time afterward, a sort of cosmic echo of a place that has already, in the relevant call sense, departed. Astrophysicists have calculated that this entire process, for the galaxies currently nearest the edge of our observable universe, will play out gradually over the next 100 billion years or so, meaning that even in the deepest of deep futures we will discuss in this documentary, distant galaxies are not vanishing in a flash, but fading like the last embers of a fire, growing dimmer and redder for unimaginable stretches of time before truly falling silent. This is also why, even though we have established that the ultimate fate of unbound galaxies is to vanish beyond our cosmic horizon, that fate will not be evident to any observer over a human lifetime, a human civilization's lifetime, or even a span of time many, many times longer than the current age of the universe itself. We are not watching this happen in real time. We are describing the mathematics of a process so slow that it makes the 13.8 billion years since the Big Bang look like the opening seconds of a much longer story. That raises an obvious and important question. If this all takes place across mind-bending stretches of time, how do astronomers actually have any confidence in these predictions at all? There is something almost paradoxical about a scientific prediction that, by its own description, cannot be confirmed by any observation made within the lifetime of our species, our planet, or quite possibly any civilization that exists at any point in cosmic history. So it's worth pausing to understand exactly what kind of evidence underlies this picture, because it is not speculation in the casual sense. It is extrapolation built from several independently measured pillars. The first pillar is the measured expansion rate itself, the Hubble constant, derived from multiple independent techniques. The redshift of distant supernovae, the brightness of variable stars called Cepheids, ripples in the cosmic microwave background left over from the early universe, and the gravitational behavior of galaxy clusters. These methods don't agree perfectly with each other, a persistent and genuinely debated discrepancy in cosmology, sometimes called the Hubble tension. But they agree closely enough to establish, with high confidence, that expansion is happening, and roughly how fast. The second pillar is the measured acceleration of that expansion, established by the 1998 supernova surveys, and reinforced by 2 decades of subsequent observations, including detailed mapping of the cosmic microwave background by missions like WMAP and Planck, and large-scale galaxy surveys that map the distribution of matter across billions of light years. The third pillar is general relativity itself, Einstein's theory of gravity, which has been tested with extraordinary precision in numerous settings, from the orbit of Mercury to the detection of gravitational waves from colliding black holes, and which provides the mathematical framework, connecting the measured expansion rate to predictions about cosmic geometry and ultimate fate. When you combine a well-tested theory of gravity with precisely measured values for how much matter, and dark energy the universe contains, and how fast it is currently expanding, you can run the equations forward in time. The same way an astronomer can calculate exactly where a comet will be decades from now, based on its current position and velocity, combined with the laws of orbital mechanics. The honest caveat, and this documentary will return to it more than once, is that the prediction's reliability depends entirely on dark energy continuing to behave the way our current measurements suggest it behaves. If dark energy's strength is genuinely constant over cosmic time, the way Einstein's original cosmological concept assumed, then the accelerating expansion we've described continues indefinitely, and the picture of vanishing galaxies holds. But some theoretical models propose that dark energy's strength could change over time, weakening, strengthening, or even eventually reversing. And if any of those alternative models turn out to be correct, the long-term fate of the cosmos could look meaningfully different from the picture currently favored by the data. Current observations, including recent results combining multiple large galaxy survey datasets, are consistent with dark energy behaving as a constant, but with uncertainties still large enough that more exotic possibilities have not been ruled out. This is one of the most active and important open questions in modern cosmology, and missions and surveys over the coming decade are specifically designed to narrow down the answer. For the remainder of this documentary, we will follow the standard model: constant dark energy, eternal acceleration, because it remains the best supported picture based on current evidence. But it is worth remembering, as we travel further into deep time, that we are extrapolating a well-supported trend across timescales so enormous that even small uncertainties in our starting measurements compound into significant differences in the details, even if the broad outline remains the same. There is also a subtler kind of confidence at work here, one that doesn't depend on dark energy specifically. Even setting dark energy aside entirely, the basic mathematics of an expanding universe populated by gravitationally bound and unbound structures was understood, in broad outline, decades before the 1998 acceleration discovery. Cosmologists already knew that distant, unbound galaxies would eventually become unreachable in any universe that continued expanding indefinitely, simply because of how quickly distances grow relative to the fixed speed of light. The 1998 discovery did not invent this future. It accelerated it and made it considerably more certain, by demonstrating that the expansion would not slow down and reverse, as some earlier Big Crunch models had proposed, but would instead continue and intensify indefinitely. This means the broad narrative of this documentary: galaxies separating into isolated, gravitationally bound islands, surrounded by a horizon that grows to claim more of the universe over time, was already a plausible outcome under several pre-1998 cosmological models. What changed with the discovery of acceleration was not whether this kind of future was possible, but how confident scientists could be that it is, in fact, the future we are actually living toward, rather than one of several competing possibilities that might equally have come to pass. It is this layering of independent evidences, multiple expansion rate measurements agreeing in broad terms, multiple confirmations of acceleration across different observational techniques, and a theory of gravity tested with extraordinary precision in countless other contexts that allows cosmologists to speak about events tens and hundreds of billions of years in the future with genuine scientific confidence, even while fully acknowledging that no one will ever be present to confirm the prediction directly. This is, in its own way, one of the more remarkable achievements of modern science. The ability to describe, with mathematical precision, an event that lies so far beyond any possible human witness that even the concept of soon or eventually barely retains its ordinary meaning. So far, we have described transformation mathematically. Redshift, recession velocity, horizon distance. But the title of this documentary makes a visual promise, and it deserves a visual answer. What would someone, standing on a hypothetical world, looking up at a hypothetical sky, actually see at different points across this multi-billion-year transition? Tonight, from Earth, a sufficiently dark, unpolluted sky reveals roughly 20,500 to 3,000 individual stars visible to the naked eye, all of them residents of our own Milky Way, plus a handful of smudges that are not stars at all but entire other galaxies. The Andromeda galaxy, faintly visible without a telescope under the right conditions, along with the large and small Magellanic Clouds, dwarf companion galaxies visible primarily from the southern hemisphere. With a telescope, that handful expands into thousands of additional visible galaxies. And with the deepest instruments available to professional astronomy, into the hundreds of billions we have already discussed, 1 trillion years from now. A number so large it is worth simply sitting with for a moment, representing roughly 70 times the current age of the universe. The picture changes dramatically. By this point, the local group merger will have long since completed. Milkomeda, our descendant galaxy, will have absorbed essentially every other member of the local group, and every galaxy beyond that merged structure will have receded so far and redshifted so completely that it will have crossed entirely beyond detectability, even with instruments far more sensitive than anything humanity currently possesses. An observer standing on a world somewhere within Milkomeda, looking outward into the space between galaxies, would see nothing. Not faint lit nothing. Not very dark but technically present nothing. Genuinely, permanently undetectable nothing. No matter how long they observed, no matter how sensitive their instruments became, because the light that would reveal those other galaxies will have either already arrived and faded past detection, or will never arrive at all, having been launched from a point already beyond that observer's cosmological horizon. Looking inward, toward their own galaxy, the sky would actually remain reasonably rich, full of the stars that make up the merged Milkomeda structure, since those stars remain gravitationally bound and visible to each other regardless of the universe's overall expansion. The strangeness would not be an empty sky in every direction. It would be a sky with a sharp, almost binary quality to it, densely populated in the direction of one's own galaxy, and utterly, featurelessly blank in every direction beyond it. This detail matters because it corrects a common misconception about the far future of the universe. The popular image of heat death often implies a universe that becomes uniformly, totally dark and empty everywhere, all at once. The actual picture, at least at the trillion-year mark, is more specific and, in its own way, stranger, isolated, internally rich islands of light, merged galaxies like Milkomeda, drifting through a surrounding void so complete that each island would have absolutely no way of detecting any other island's existence. A civilization existing within one of these islands, with no records of the deep past, no knowledge of the universe's earlier, richer history, might reasonably conclude that their galaxy was the only structure that had ever existed. Not due to any cosmic conspiracy, but simply because every form of evidence to the contrary would by then be permanently and physically unreachable. This is one of the more genuinely unsettling implications of accelerating expansion. The universe is not merely going to become harder to study in the deep future. It is going to become, for any observer trapped within an isolated galactic island, fundamentally and permanently unknowable beyond the boundary of their own galactic home. We will return to this idea, what it would mean to be a future observer, cut off from the wider universe, in more detail later in this documentary. For now, it is enough to recognize that the disappearance described in our title is not a single event, but a gradual, multi-stage unraveling, with the sky changing meaningfully across timescales of millions, then billions, then trillions of years, each stage stranger and emptier than the one before it, until what remains is not a dark sky in every direction, but a brilliant, isolated home surrounded by an unreachable, undetectable everything else. There is a sobering thought embedded in everything we've discussed so far, and it deserves its own moment of reflection before we move further into the deep future. The universe we observe tonight, full of visible galaxies stretching back billions of years, may represent an unusually generous window in cosmic history, a window that is already, slowly, closing. Consider how different the sky would have looked, and will look, at other points in cosmic time. In the very early universe, within the first few 100 million years after the Big Bang, there were no galaxies at all in the modern sense. This period is sometimes called the Cosmic Dark Ages, a stretch of time after the initial flash of the Big Bang's radiation had faded into the cosmic microwave background, but before the first stars had ignited to produce new light. The universe during this era was, by definition, dark, filled with hydrogen and helium gas, slowly being pulled together by gravity, but not yet producing any starlight of its own. Then came the formation of the first stars and galaxies, beginning what we called earlier the stelliferous era. And it is genuinely worth appreciating that we exist within this era rather than before it or after it. We are not at the universe's beginning, and we are nowhere near its end, but we are positioned within the relatively narrow slice of cosmic history, during which the sky is full of visible structure, stars being born, galaxies colliding and merging, light pouring across unimaginable distances, and somehow still arriving in time to reach our telescopes. Crucially, the era of maximum galaxy visibility may already be behind us. Astronomers studying the history of star formation across the universe have found that the overall rate of new star birth peaked roughly 10 billion years ago and has been gradually declining ever since, a trend sometimes summarized as the universe being in its stellar twilight, past its brightest days, even though that twilight will stretch on for trillions of years to come. At the same time, the accelerating expansion driven by dark energy means that the number of galaxies within our observable horizon, and the brightness of distant galaxies generally, has been slowly and steadily decreasing for billions of years, even as new stars continued to form within our own and nearby galaxies. In other words, the night sky was, in a meaningful astronomical sense, more crowded with visible structure in the deep past than it is today, and it will be less crowded a billion years from now than it is today. We are living somewhere on a long, slow downward slope, not at the peak and very far from the bottom, but undeniably past the richest period the universe has ever offered an observer. This is not a cause for despair. If anything, it is a reason for a particular kind of gratitude, the kind reserved for witnessing something genuinely temporary, most of the universe's eventual history, and we are about to journey through almost all of it, will be far darker, far emptier, and far less hospitable to anything resembling an observer at all. We exist precisely during the window when galaxies still burn brightly enough and are still close enough to be seen, studied, and wondered about. That window will not close abruptly. It will close the way long summer evenings shorten into autumn, almost imperceptibly, day by day, until one day, far in the future, someone or something might notice that the sky looks different than it once did. To understand exactly how that closing unfolds, we need to start moving the clock forward. First by millions of years, then billions, then trillions, and watch, chapter by chapter, what each stage of this transformation actually looks like. Before we journey to the truly distant future, there is a much nearer event worth understanding in detail, because it previews, on a much smaller and more personal scale, the broader story of cosmic isolation that the rest of the universe will eventually experience. The Andromeda Galaxy, our nearest large galactic neighbor, sits roughly 2.5 million light-years away, itself a staggering distance, and yet, on the scale of cosmic structure, practically next door. Unlike the vast majority of galaxies in the universe, Andromeda is not receding from us. It is approaching, falling toward the Milky Way under the mutual gravitational pull between the two galaxies, at a speed of roughly 110 kilometers per second. This single fact, that our nearest major galactic neighbor is moving toward us rather than away, is sometimes presented as a curiosity, but it is actually a direct demonstration of everything we discussed earlier about bound versus unbound systems. Andromeda and the Milky Way are close enough and massive enough that their mutual gravity has always overwhelmed any influence from the expansion of space between them. They have been gravitationally bound to each other, essentially, since not long after they formed. Current models, refined using precise measurements of Andromeda's sideways motion from the Hubble and Gaia space telescopes, suggest that the two galaxies will begin to merge in roughly 4 to 4.5 billion years. Coincidentally, around the same time our own sun is expected to swell into a red giant and dramatically reshape the inner solar system, a separate and equally fascinating story for another documentary entirely. The merger itself will not resemble a collision, in the way two solid objects might collide. Galaxies are mostly empty space. The stars within them are separated by distances so vast that the probability of any two individual stars actually colliding during the merger is exceedingly small. Instead, the two galaxies will pass through and around each other repeatedly over a period of roughly 2 billion years, their gravity distorting each other into long tidal streams and arcs, triggering bursts of new star formation as gas clouds are compressed and shocked, before eventually settling into a single, larger elliptical galaxy. Astronomers have given this hypothetical merged galaxy the informal nickname Milkomeda, and simulations suggest it will be a massive elliptical galaxy quite different in structure from either of its spiral progenitors. Smoother, more uniformly distributed, the dramatic spiral arms of both original galaxies, erased by the violence and slowness of repeated gravitational interaction. Other members of the local group, including the Triangulum galaxy and dozens of smaller dwarf galaxies, will likely be drawn into this merger as well, over a considerably longer timescale, extending perhaps tens of billions of years into the future, gradually consolidating almost everything gravitationally bound to us into one final, large galactic structure. Here is the detail that connects this story directly back to our central theme. Once that merger is complete, and once the more distant unbound galaxy clusters have receded far enough to fade beyond detection, Milkomeda will essentially be alone, an island galaxy in an empty sea, with no other major galaxy close enough or gravitationally connected enough to ever be visible from within it again. A civilization living inside that future merged galaxy. And there is no reason, in principle, why intelligent life could not exist at that point, long after our sun has died, would look up at a sky containing essentially zero other galaxies. Not because galaxies do not exist elsewhere, but because every other galaxy will, by then, have receded beyond the cosmological horizon we discussed earlier, leaving Milkomeda as one of the last visible witnesses to a universe that was once full of countless visible neighbors. This is, in miniature, the entire trajectory of this documentary. Companionship through gravity, isolation through expansion, and a sky that empties out not through destruction, but through separation so vast and so permanent that it amounts to the same thing. Beyond our local group lies a much larger structure that offers another important data point in understanding how cosmic isolation will unfold. The Virgo cluster, a collection of more than 1,000 galaxies located roughly 54 million light-years away, and the gravitational anchor of an even larger structure called the Virgo supercluster, or Laniakea, which includes our own local group as a relatively minor outlying member. Unlike Andromeda, the Virgo cluster is too far away, and the gravitational connections are too weak relative to the expansion of space for it to ever merge with our local group. The Virgo cluster is, in the terminology we established earlier, unbound from us, meaning that, despite its gravitational influence having a measurable slowing effect on our local expansion, dark energy's stretching effect will eventually win, and the distance between us and Virgo will increase indefinitely. This matters because the Virgo cluster represents the threshold case, the dividing line between what stays and what eventually leaves. Galaxy clusters and superclusters across the universe sit in a similar position, gravitationally significant on the scale of millions of light years, but ultimately insufficient to resist the relentless stretching operating on scales of hundreds of millions and billions of light years. The broader structure that all of these clusters belong to is sometimes called the cosmic web, an enormous, lattice-like arrangement of galaxy filaments sheets, and clusters, separated by vast, nearly empty regions called voids. This structure was first mapped in detail through large galaxy surveys, beginning in the 1980s, and refined dramatically since, revealing that galaxies are not distributed randomly throughout space, but rather trace out a pattern that looks, on the largest scales, almost like a biological structure. Strands and nodes and gaps, sculpted over billions of years by the gravitational pull of both ordinary matter and the much more dominant dark matter. The cosmic web's filaments and nodes represent regions where gravity has, so far, successfully fought back against expansion, pulling matter together into denser structures. Even as the overall volume of the universe, between those structures, continues to grow. But so far is the operative phrase. As dark energies influence compounds over the coming tens and hundreds of billions of years, even gravitationally bound clusters like Virgo will become increasingly isolated from their neighboring structures. The voids between filaments widening, the filaments themselves stretching and thinning, the entire web slowly relaxing into emptiness, even as the clusters and superclusters at its nodes remain internally intact. The voids themselves deserve a moment of attention, because they are not simply empty space, in the way the term might suggest. Cosmic voids are enormous regions, some spanning hundreds of millions of light-years across, where the density of galaxies is dramatically lower than the cosmic average, though rarely zero. They were not carved out by any explosive process. They are the natural result of gravity's long, patient work, pulling matter out of underdense regions and concentrating it into the filaments and nodes that define the cosmic web. The largest mapped void structures, with names like the Butes void, already span distances so large that light takes hundreds of millions of years simply to cross from one side to the other. What makes voids relevant to our story is that the entire universe, over sufficiently long timescales, is trending toward looking more like a void and less like a filament. As accelerating expansion continues, the relative volume occupied by genuinely empty space increases, while the volume occupied by gravitationally bound structure, already a small fraction of the total, shrinks further still, not because matter is being destroyed, but because the space surrounding it is being created far faster than gravity could ever hope to fill. A useful, if imperfect, way to picture the very far future is to imagine the entire structure of the cosmic web stretched out the way the voids are today. Islands of bound galaxies, like our future Milkomeda, skid through what is functionally one enormous, near-total void, with the filaments that once connected them having stretched into irrelevance. This gives us a clearer picture of the intermediate future, somewhere beyond the next few tens of billions of years, a universe where matter is increasingly clumped into isolated islands, merged galaxy groups like our eventual Milkomeda, isolated superclusters like an evolved Virgo, separated by stretches of genuinely empty space, so vast that, even at the speed of light, no signal will ever cross from one island to another again. It is worth pausing here to register the scale of what we are describing. We have moved, in the span of a few chapters, from a universe currently containing an estimated hundreds of billions of galaxies within our observable horizon, a number itself revised downward in recent years from earlier estimates that ran into the trillions, following more careful analysis of deep imaging surveys, toward a future in which the visible universe, for any observer anywhere, will eventually contain only a single merged galactic island, surrounded by nothing. That revision in estimated galaxy count is itself a small but illuminating story about how this kind of science actually works. For years, the widely cited figure, drawn from analysis of deep Hubble Space Telescope images and statistical modeling of how many faint, undetected galaxies likely exist below current detection thresholds, suggested the observable universe might contain somewhere around 2 trillion galaxies. More recent analysis, incorporating updated data from deep field surveys and refined accounting for how galaxy brightness and size are distributed, has pulled that estimate back down closer to a few hundred billion, demonstrating that even foundational numbers in cosmology remain subject to revision as observational techniques improve. The broader trajectory we have described, isolation, separation, eventual disappearance beyond the horizon, does not depend on getting that exact count right, but the correction is a useful reminder that this entire field operates by continuously refining its picture. As better instruments and better statistics become available, rather than treating any single number as final. What remains constant, regardless of exactly how many galaxies populate the observable universe today, is the underlying trend. A slow, continuous contraction of how much of the universe will ever be reachable again, layered on top of the entirely separate and already occurring decline in how many new stars are being born within the galaxies that remain. Both processes are running simultaneously on different timescales, and both point toward the same eventual destination. A universe that, structurally, becomes simpler, sparser, and quieter the further forward in time you look. That is not the end of the story. It is, in fact, only the first major milestone in a transformation that will continue for a length of time so vast that all of human history, all of Earth's geological history, and the entire current age of the universe will eventually look, by comparison, like the very first instant of an extraordinarily long story. We now have the foundational pieces we need to travel forward in time with confidence rather than guesswork. We understand that the expansion of space, not the motion of galaxies through space, is the engine behind everything that follows. We understand that this expansion is accelerating, driven by a form of energy embedded in the vacuum of space itself that we call dark energy, and that this acceleration appears, based on every measurement currently available, to be a permanent and ongoing feature of our universe rather than a temporary phase. We understand the crucial distinction between gravitationally bound systems, like our local group, which will survive together as merged structures, and unbound systems, like the Virgo cluster and every more distant galaxy, supercluster, and filament, which will recede from us and from each other forever. And we understand the cosmological event horizon, the genuinely strange, genuinely real boundary beyond which light can never again reach us, a boundary that is slowly, continuously expanding to claim more and more of the currently visible universe. What we have not yet done is walk through, chapter by chapter, exactly what each stage of this transformation will look like, not just for distant unbound galaxies, but for our own eventual Milkomeda, for the stars within it, and ultimately for the very structure of matter and energy that makes up everything we have discussed. That journey takes us across almost incomprehensible spans of time, From the remaining trillions of years of active star formation, through the gradual dimming of the stelliferous era as the last new stars flicker out, into an age dominated by dead stellar remnants, slowly cooling in the dark, and finally towards speculative possibilities at the very edges of theoretical physics. Proton decay, black hole evaporation, and the genuinely open question of how, or whether, the universe's story ends at all. We have also not yet fully confronted the most personal version of this question. What would it actually mean for any future observer? Biological, artificial, or something we cannot currently imagine. To live inside that future, isolated galaxy, looking up at a sky that contains only the stars of their own galactic home, with no other galaxy, no other light, no other evidence that anything else ever existed beyond the boundary of their own night sky. That is where we are going next. Deeper into the timeline, deeper into the physics, and deeper into what it would actually feel like to witness the universe's slow, quiet transition from a place full of visible neighbors into the silent, isolated, but still extraordinary place it is destined to become. There is a particular kind of perspective shift worth carrying forward into the next part of this journey. Everything we have described so far, the redshifting, the horizon, the merger of our local group, the slow unraveling of the cosmic web, unfolds across timescales already difficult to hold in the mind. 100 billion years is roughly 7 times the current age of the universe. 1 trillion years is roughly 70 times its current age. And yet, as vast as these numbers are, they represent only the earliest chapters of the universe's full story, not its conclusion. Stars, even the longest lived among them, are not eternal. The red dwarf stars that make up the majority of any galaxy's stellar population, small, dim, and remarkably efficient at conserving their nuclear fuel, are projected to continue burning for trillions of years before exhausting their hydrogen, a lifespan so long that not a single red dwarf star has died of old age anywhere in the universe since the Big Bang. Every one currently observed is still in the prime of an extraordinarily long life. Eventually, even they will fade. New star formation, already declining from its peak roughly 10 billion years ago, will continue to slow as the raw material for new stars. Primarily hydrogen gas is gradually locked away inside stellar remnants, consumed by star formation, or ejected from galaxies entirely by gravitational interactions and supernova-driven outflows. What happens after the last star forms, after the last red dwarf exhausts its fuel, after Milkomeda settles into its final isolated form? And what becomes of matter itself across timescales so vast that even trillions of years are a rounding error, is the territory we will explore. Next, it is a future stranger, quieter, and in its own way more profound than anything we have covered so far. An age of stellar remnants slowly cooling in an empty universe, a possible age of black holes consuming everything that remains. And finally, at the furthest edges of current theoretical physics, genuine open questions about whether matter itself is permanent, or whether even the particles that make up stars, planets, and observers are subject to a kind of decay so slow it would make even the time scales already discussed look instantaneous by comparison. The story is far from finished. If anything, the truly strange part is only beginning. This is where our journey continues. Forward past the death of star formation itself, into an age of stellar corpses, slowly cooling in an ever darker universe, then into an age where the only light left comes from the violent feeding of black holes, and finally to the genuine edge of what physics can currently tell us. A place where matter itself may not be permanent, and where even the most patient observer would eventually run out of universe left to observe. It is a strange kind of comfort to know that this entire future, however vast, is not pure speculation. Each step of it follows from physics already tested and confirmed in laboratories and observatories today. We are not inventing the ending. We are reading it, one careful calculation at a time, off equations that have already proven themselves trustworthy. Everywhere else they've been checked, before we follow the stars themselves into their long decline. There is another, even old form of light worth considering, because its fate offers a useful preview of the broader pattern this entire documentary describes. The cosmic microwave background, sometimes called the afterglow of the Big Bang itself. This radiation originated roughly 380,000 years after the Big Bang during an event cosmologists call recombination. The moment when the early universe, until then a hot, opaque plasma of charged particles, cooled enough for electrons and protons to combine into stable neutral hydrogen atoms. Before that moment, light could not travel freely. It was constantly scattered by the dense soup of charged particles surrounding it, the way light struggles to travel far through thick fog. After that moment, with charged particles bound up into neutral atoms, the universe became transparent, and the light present at that instant has been streaming freely through space ever since, stretched by the universe's ongoing expansion from its original, extremely hot wavelength down to the faint microwave radiation we detect today, registering at a temperature of just 2.7 degrees above absolute zero. The cosmic microwave background was first detected, somewhat by accident, in 1965 by Arno Penzias and Robert Wilson, who initially mistook the persistent background noise in their radio antenna for a flaw in their equipment before realizing they had stumbled onto direct observational evidence of the Big Bang itself, a discovery that earned them the Nobel Prize in Physics in 1978, and that remains one of the strongest pillars of evidence supporting the entire Big Bang model of cosmology. This ancient light is, in a sense, the ultimate example of the red-shifting and dimming process described throughout this documentary, just already far along that path. It has been stretching for the entire history of the universe, and it will continue to stretch indefinitely into the future, following exactly the same physics responsible for the eventual disappearance of distant galaxies. As the universe continues expanding, the cosmic microwave background's temperature will continue to drop, its wavelength continuing to lengthen, eventually stretching so far that it becomes utterly undetectable by any conceivable instrument, blending into an undifferentiated, vanishingly faint background indistinguishable from empty space itself. There is something fitting in this detail. The very first light the universe ever produced, the radiation that allows us today to look back and directly observe conditions just a few 100,000 years after the Big Bang, is undergoing the same slow fade that will eventually claim every galaxy's light as well. The universe's oldest message to itself and the light from its youngest, most distant visible structures are both ultimately headed toward the same destination, a stretch so complete that no trace of the original signal remains detectable, even though, in the strictest physical sense, the light itself never technically stops existing. It simply becomes redshifted into complete and permanent undetectability. This single example also illustrates something important about how cosmologists think about the difference between something ceasing to exist and something becoming permanently undetectable. Throughout this documentary, and particularly in the chapters ahead, that distinction will matter again and again. Very little in this story is destroyed outright. Almost everything described here undergoes the much quieter, much stranger process of simply becoming unreachable. Present, in some technical sense, somewhere in the vast expanse of ever-growing universe, but utterly beyond the possibility of detection by any observer, anywhere, ever again. We are currently living inside what astronomers call the stelliferous era, the age of starlight, spanning from roughly a few 100 million years after the Big Bang to an estimated end point somewhere around 100 trillion years from now. We are, cosmically speaking, still near the very beginning of it, even though it already feels, from a human vantage point, impossibly old. The defining feature of this era is straightforward. Galaxies contain enough hydrogen and helium gas, distributed in cold, dense clouds, for gravity to keep collapsing pockets of that gas into new stars. New stars mean new light, new heavy elements forged in stellar cores and supernovae, and, at least within our own corner of the universe, the chemical raw materials that eventually make planets, oceans, and living things possible. This process, however, is not self-sustaining. Every time a star forms, it locks away some fraction of the available gas, either permanently, in the case of low-mass stars that will burn for trillions of years, or temporarily, in the case of massive stars that explode and return some material to the surrounding gas, though never all of it. Over enough generations of star formation, galaxies gradually run out of the raw material needed to make new stars, the way a campfire gradually runs out of wood, even while individual logs are still burning. Observational evidence already shows this decline underway. The rate of star formation across the universe peaked roughly 10 billion years ago, a period sometimes called cosmic noon, and has been falling fairly steadily ever since, a trend confirmed by surveys tracking star formation activity across galaxies at different distances, and therefore different points in cosmic history. Our own Milky Way today forms new stars at only a fraction of the rate it once did, and most large galaxies show a similar pattern. Vigorous star formation in their youth, tapering gradually as available gas is consumed or expelled. The observational case for this cosmic decline is worth understanding in a little more detail, because it rests on some genuinely clever astronomy. Astronomers cannot watch a single galaxy across billions of years, since the timescales involved exceed not just human lifespans, but the entire history of our species, by many orders of magnitude. What they can do instead is observe many different galaxies at many different distances. And since light takes time to travel, a galaxy a billion light-years away is seen as it appeared a billion years ago, while a galaxy 5 billion light-years away is seen as it appeared 5 billion years ago. By studying large samples of galaxies at progressively greater distances, and therefore progressively earlier cosmic times, astronomers can reconstruct a statistical picture of how the universe's collective star formation rate has changed over cosmic history. This technique, combined with data from surveys using instruments ranging from the Hubble Space Telescope and the Spitzer Space Telescope to radio observatories like the Atacama Large Millimeter Array in Chile, which can detect the cold, dense gas clouds that serve as the raw material for star formation in galaxies across cosmic history, has produced a remarkably consistent picture. A universe whose star-forming activity rose steeply in its early billions of years, reached a broad peak around 10 to 11 billion years ago, and has since declined to a rate perhaps 10 times lower than that peak, in what seems to be a continuing trend rather than a plateau. The Atacama Large Millimeter Array, in particular, has proven enormously powerful for this kind of work, capable of detecting the molecular gas reservoirs in distant, early galaxies that mark regions of active or imminent star formation with a sensitivity no previous instrument could match. The expulsion mechanism deserves particular attention, because it turns out to be just as important as consumption. Massive stars end their lives in supernova explosions, violent enough to blast surrounding gas out of a galaxy's gravitational grip entirely, and supermassive black holes at galactic centers can drive powerful outflows of their own, heating and expelling gas that would otherwise eventually cool and collapse into new stars. Galaxy mergers, including the one our own Milky and Andromeda are destined for, can also trigger intense bursts of star formation by colliding and compressing gas clouds, but they tend to do so at the cost of using up a large fraction of the remaining fuel relatively quickly, accelerating the galaxy's eventual transition into a quieter, gas-poor state. This is part of why the eventual merger between the Milky Way and Andromeda, discussed in detail earlier, carries a certain bittersweet quality once you understand the full picture. The collision will likely trigger a temporary increase in star formation, a final, dramatic burst of new stellar birth, as gas clouds from both galaxies are violently compressed together. But that burst will also hasten the depletion of the combined galaxy's remaining gas supply, pushing Milkomeda more quickly toward the quieter, increasingly barren state that all sufficiently old galaxies eventually reach. Current models project that meaningful star formation across the universe, defined as galaxy still producing new stars at rates comparable to anything happening today, will likely continue for somewhere between 1 trillion and 100 trillion years, depending on how efficiently the remaining gas reservoirs in galaxies are consumed, recycled, or lost. The wide range in that estimate reflects real scientific uncertainty about processes like gas recycling. The way some material expelled by dying stars eventually cools and falls back inward, available for a future generation of star formation, which is difficult to model precisely across such enormous timescales. What is not in serious doubt is the eventual destination, even if the exact arrival time remains somewhat uncertain. A future in which the available hydrogen for new star formation is, for all practical purposes, exhausted, and the galaxies that remain, by then, almost entirely the merged, isolated islands like Milkomeda, will contain only the stars they already have, slowly aging with no meaningful replacement on the way. If you wanted to know which stars will be the very last ones still shining when the stelliferous era finally closes, the answer is almost certainly not the bright, dramatic stars that dominate our intuitive picture of the night sky. The brightest, most massive stars, blue giants and supergiants, the kind that produce dramatic supernovae and briefly outshine entire galactic regions, are also the shortest-lived, burning through their nuclear fuel in a few million years before exploding or collapsing. They are spectacular, but cosmically speaking, almost instantaneous. The stars that will outlast everything else are the opposite kind, Small, dim, unremarkable red dwarfs with masses as low as roughly 8% of our Sun's mass, near the theoretical minimum needed to sustain hydrogen fusion at all. These stars burn their fuel with extraordinary efficiency, partly because their lower internal temperatures and pressures slow the fusion reactions dramatically, and partly because, unlike our Sun, they are fully convective, meaning their internal material continuously circulates, bringing fresh hydrogen from the outer layers into the fusing core, rather than leaving large reserves of unused fuel stranded in an inert outer shell. The practical result of this efficiency is staggering longevity. While our Sun, a fairly average star, will exhaust its core hydrogen and begin transforming into a red giant in roughly 5 billion years, the smallest red dwarfs are projected to continue fusing hydrogen for trillions of years. Current estimates for the very smallest range from roughly 1 trillion years, up to as much as 10 trillion years or more, depending on the star's exact mass and the details of stellar physics models, which remain difficult to fully verify since, as mentioned earlier, not a single red dwarf has actually completed its life cycle since the universe began. Every red dwarf currently observed anywhere in the cosmos is, relatively speaking, still in its infancy. This single fact reframes how we should think about the end of starlight. It will not arrive as a dramatic blackout. It will arrive as an extraordinarily long, almost imperceptible fade, with the smallest and dimmest stars, the ones least likely to be noticed by any observer today, quietly outlasting every more spectacular star by a factor of hundreds or even thousands. When a red dwarf finally does exhaust its hydrogen fuel after trillions of years, the ending is also notably undramatic compared to the explosive deaths of larger stars. Models suggest these stars will gradually contract and heat as their fuel runs low, briefly becoming somewhat hotter and bluer, before settling into a slow, final collapse into a white dwarf, a dense, Earth-sized remnant composed primarily of helium, no longer generating energy through fusion, instead simply radiating away its remaining heat into the surrounding darkness over a further span of time stretching into the trillions upon trillions of years. It is worth pausing on the strangeness of this image. Stars that, by the time they finally die, will have outlived not just every human civilization, not just the entire current age of the universe, but the entire current age of the universe repeated hundreds of times over. And even then, dying does not mean disappearing. It means transitioning into a different, quieter kind of existence, one we will explore in detail in the chapter that follows. Astronomers and cosmologists have given a name to the period that follows the end of meaningful star formation. Once the last red dwarfs have exhausted their fuel and the last stellar nurseries have run dry of gas, the degenerate era. The name comes from physics, not biology or morality. Degenerate matter is a technical term describing matter held up not by ordinary thermal pressure, the kind of pressure that comes from particles moving and colliding due to heat, but by quantum, mechanical effects that prevent certain particles from being squeezed too closely together. This is precisely the state of matter found inside white dwarfs, neutron stars, and, in a more extreme sense, inside black holes themselves, by the time the degenerate era is in full swing. A period astronomers estimate will last from roughly 1 trillion years after the Big Bang out to perhaps 10 to the 40th power years, a number so large that it functionally defies ordinary comprehension. the population of objects within any given galaxy will have transformed almost completely. Where the galaxy once contained a vibrant mixture of bright main sequence stars, glowing gas clouds, and occasional dramatic supernovae, it will instead consist almost entirely of stellar remnants. White dwarfs, neutron stars, and black holes, along with the rocky and gaseous planets, if any survive, that once orbited the stars now reduced to these dense, dark husks. White dwarfs, the most common remnant, will not remain hot and visible forever, though their cooling proceeds on a timescale almost as staggering as the lifespan of the red dwarf stars they came from. A typical white dwarf radiates away its residual heat slowly, over trillions of years, gradually fading from a faintly glowing ember into what physicists call a black dwarf, a cold, dark stellar remnant no longer emitting any meaningful light, roughly the temperature of the surrounding universe itself. No black dwarf currently exists anywhere in the observable universe. For the same reason, no red dwarf has yet died. The universe, at 13.8 billion years old, simply has not existed long enough for any white dwarf to finish cooling. The first black dwarfs are not expected to form until roughly 10 to the 15th power years from now, a number that makes even the trillion-year timescales discussed earlier look comparatively immediate. Neutron stars, the ultra-dense remnants left behind by the explosive deaths of more massive stars, so compact that a teaspoon of their material would weigh roughly as much as a mountain, will similarly cool over enormous timescales, eventually becoming cold, dark, and essentially invisible except through their residual gravitational influence, and, in some cases, their rotation, which can persist as detectable radio pulses. These are the objects we currently observe as pulsars, for extraordinarily long periods before gradually slowing and fading as well. There is a third, often overlooked category of object that will also populate the degenerate era in significant numbers. Brown dwarfs, sometimes described as failed stars, objects too low in mass to sustain the kind of stable, sustained hydrogen fusion that defines an ordinary star, yet still substantial enough to generate some warmth through gravitational contraction and limited fusion of heavier hydrogen isotopes early in their existence. Brown dwarfs are already common throughout the present-day universe, though their dimness makes them difficult to detect compared with ordinary stars. Over the kind of timescales discussed in this chapter, brown dwarfs will cool gradually, much like white dwarfs, but from a much lower starting temperature, eventually joining the broader population of cold, dark substellar objects drifting through Milkomeda's increasingly quiet interior. The fate of planets during this era is similarly worth a brief mention, since it connects this cosmic scale story back to something more intimate. Any planet still orbiting a star at the time that star exhausts its fuel faces a complicated set of possible outcomes, depending heavily on the original star's mass and the planet's distance from it. Some planets, particularly those orbiting close to stars destined to expand into red giants, will likely be engulfed entirely during that expansion phase, their material absorbed into the dying star's swollen outer layers. A fate current models suggest may await Mercury, Venus, and very possibly Earth itself, when our own Sun reaches the end of its main sequence life in roughly 5 billion years. Other planets, orbiting at greater distances or around stars that shed their outer layers more gently, may survive in some form, ending up in orbit around the resulting white dwarf or neutron star, slowly cooling alongside their stellar remnant for the remainder of cosmic time. Still others, including planets in systems disrupted by the close gravitational encounters and ejections discussed elsewhere in this chapter, may be flung out of their home systems entirely, becoming what astronomers call rogue planets, worlds with no host star at all, drifting alone through interstellar and, eventually, intergalactic space. And black holes, objects whose gravity is so extreme that not even light can escape from within a certain boundary. The event horizon we discussed conceptually in Part 1 will, during this era, become increasingly dominant. Not because more of them are forming, but because they are remarkably good at surviving. Unlike white dwarfs and neutron stars, which slowly radiate away their heat and fade, black holes are expected to remain almost entirely unchanged on these timescales, patiently growing slightly through the accretion of whatever stray matter wanders close enough to be captured. The picture that emerges, then, is of a galaxy, our future Milkomeda among them, gradually transforming from a brilliant, star-filled structure into something closer to a graveyard, a vast collection of cold, dark stellar remnants, drifting in mutual orbit, occasionally interacting gravitationally, with black holes slowly consolidating an increasing share of the galaxy's mass, while everything else fades toward the same featureless darkness that by then will define most of the universe beyond the galaxy's boundary as well. It is tempting, at this point in the story, to imagine total and immediate darkness, but the degenerate era is not without its own strange and occasionally dramatic events. Moments when the slow, quiet decline is briefly interrupted by genuinely spectacular physics. Even in an era defined by decline, the universe does not go quietly the entire way. Across the unimaginable stretch of the degenerate era, certain rare events will continue to punctuate the darkness, not often enough to meaningfully slow the broader trend toward emptiness, but often enough to remain genuinely fascinating moments of activity in an otherwise increasingly silent cosmos. One such event is the occasional collision between two white dwarfs, drawn together over trillions of years by the same kind of gradual gravitational interactions that, on a vastly shorter timescale, are currently drawing the Milky Way and Andromeda together. If two white dwarfs collide with sufficient combined mass, the result can be a Type Ia supernova, the same kind of standardized stellar explosion discussed in Part 1, the one that first revealed the universe's accelerating expansion. Remarkably, this means that even in the unfathomably distant future, long after ordinary star formation has ceased entirely, the universe may still occasionally produce supernovae, not from young, massive stars exploding at the end of short, dramatic lives, but from ancient stellar remnants finally colliding after drifting through the dark for spans of time longer than the current age of the universe many times over. It is worth pausing to appreciate the particular strangeness of that image. A Type Ia supernova, one of the most luminous events in modern astronomy, capable of briefly outshining its entire host galaxy, visible across billions of light-years, used by cosmologists as precision tools for measuring cosmic expansion, will, in the distant future, occasionally flare into existence, not as the grand finale of a young, vigorous star's life, but as the result of two cooling, darkening stellar corpses drifting toward each other through a nearly lightless void finally meeting after an isolation lasting longer than the universe has currently existed, and releasing in a final moment all the energy their shared material is capable of producing. The event itself would look, to any conceivable observer, anywhere near enough to detect it, indistinguishable from the Type Ia supernovae we observe today. Only the context, the surrounding darkness, the absence of other stars, the unimaginable age of the remnants involved, would mark it as something categorically different. A second source of rare illumination comes from stellar remnants occasionally wandering too close to a black hole. When this happens, the black hole's gravity can tidally disrupt the unfortunate star or remnant, tearing it apart and pulling the resulting debris into a hot, glowing accretion disk before much of the material is eventually consumed. These events, called tidal disruption events, already occur occasionally in the present-day universe and have been observed by telescopes, including the Zwicky Transient Facility, the All-Sky Automated Survey for Supernovae, and various X-ray observatories which detect their characteristic signature of a sudden brightening as infalling material heats dramatically before being consumed. They are expected to continue throughout the degenerate era, providing brief, violent flashes of light around what are otherwise the darkest objects in the cosmos, though with steadily decreasing frequency as the supply of available stellar remnants in any given region diminishes over time. There is a particularly vivid thought embedded in the tidal disruption scenario as it applies to the far future. The central black hole of our own eventual Milkomeda, having spent trillions of years in near-perfect darkness, orbited at ever-increasing distances by the last cooling stellar remnants of a once brilliant galaxy, will occasionally be interrupted by exactly this kind of event, a wandering black dwarf or neutron star, nudged too close by some gravitational perturbation, torn apart and briefly illuminating the surrounding darkness, before the material spirals inward and disappears. For great distance, if any conceivable observer existed to watch, these brief flares would mark the location of our galaxy's last active object with a precision that no other process in that era could provide. A lighthouse whose individual flashes grow rarer and rarer across the unimaginable length of the degenerate era, but that never entirely ceases until the supply of nearby material to disrupt finally runs out entirely. A third, slower process worth understanding involves the gradual gravitational evaporation of galaxies themselves. Within any galaxy, individual stars and stellar remnants are not on perfectly fixed orbits. Their paths shift slightly with each gravitational interaction with their neighbors over sufficiently long timescales. And within the degenerate era, sufficiently long means trillions upon trillions of years. These accumulated small interactions can occasionally fling individual stars or remnants outward with enough velocity to escape the galaxy's gravity entirely, ejecting them into the empty space between galaxies, now permanently isolated, with no other galaxy nearby for them to ever be recaptured by. Other objects, through the same process, will lose orbital energy instead and spiral inward, eventually merging with or being captured by the supermassive black hole that, by this point in cosmic history, will likely dominate the gravitational center of any sufficiently old, merged galaxy like Milkomeda. The combined effect of these processes, slow ejection of some matter outward, slow consolidation of other matter inward toward central black holes, means that even gravitationally bound galaxies are not perfectly stable forever. Over timescales reaching toward 10 to the 19th or 10 to the 20th power years, models suggest that galaxies like our future, Milkomeda, will gradually disperse, a meaningful fraction of their stellar remnants ejected into the surrounding void, the remainder increasingly concentrated into and around a dominant central black hole, until what was once a galaxy of hundreds of billions of stars eventually resembles something closer to a single enormous black hole, orbited by a comparatively small remaining population of stellar remnants, with a thin trail of ejected objects drifting outward into a universe that by then will offer absolutely nothing else for them to ever encounter again. This is, in its own way, one of the most genuinely melancholy images in all of cosmology. Individual stellar remnants, the cooled, dark corpses of stars that once burned brightly enough to be seen across galaxies, drifting alone through an empty universe with no possibility of ever again coming close enough to another object to interact with it in any meaningful way for the remainder of time. As the degenerate era stretches on, and as galaxies slowly disperse their stellar remnants while consolidating an increasing share of their remaining mass into central black holes, the universe gradually transitions into a period cosmologists sometimes call the black hole era, an age beginning somewhere around 10 to the 40th power years, and continuing to perhaps 10 to the 100th power years, during which black holes represent essentially the only significant astrophysical objects remaining. By this point, white dwarfs will have cooled into invisible black dwarfs. Neutron stars will have similarly faded into cold, dark remnants, any remaining ordinary matter not already consumed by a black hole will exist as isolated atoms, dust, or perhaps simple, inert structures drifting through what is, by any standard available to us today, an almost total void. The only objects producing any significant activity will be the black holes themselves, vast, patient, and, in their own strange way, the final true survivors of the era of stars. This is also where one of the strangest and most theoretically important predictions in all of physics enters the story directly. The discovery, made by physicist Stephen Hawking in 1974, that black holes are not, in fact, perfectly eternal. Hawking's calculation showed that black holes should very slowly emit a faint form of radiation, now called Hawking radiation, as a consequence of quantum effects occurring near the event horizon. The detailed physics involves the behavior of quantum fields in the curved space-time surrounding a black hole, but the practical consequence is straightforward to state, even if the underlying mechanism is genuinely subtle. Black holes slowly lose mass over time, emitting energy outward as they do, and this process, while utterly negligible on any time scale we have discussed so far, eventually leads to the complete evaporation of any black hole, given enough time. The time scale involved depends enormously on the black hole's mass, and the relationship is almost absurdly steep. More massive black holes evaporate far more slowly than smaller ones, because the rate of Hawking radiation emission decreases as mass increases. A black hole with the mass of our Sun, hypothetically isolated in empty space with nothing nearby to feed on, would take roughly 10 to the 67th power years to fully evaporate. An inconceivably long span of time, but still almost instantaneous compared to the evaporation time of larger black holes. The supermassive black holes that sit at the centers of galaxies including the one already present at the center of our Milky Way and the even larger one that will eventually anchor our future Milkomeda, contain millions or billions of times the Sun's mass and are projected to take to correspond longer to evaporate. Estimates for the largest supermassive black holes extend out to roughly 10 to the 100th power years or beyond. It's worth noting, with appropriate scientific caution, that Hawking radiation itself, while strongly supported by the underlying theoretical physics and broadly accepted within the physics community, has never been directly observed. The predicted radiation from any realistic black hole is far too faint to detect with any instrument currently available or likely to be available for the foreseeable future. The prediction rests on a combination of general relativity and quantum field theory that has passed every theoretical consistency check applied to it so far. But the complete picture of how black hole evaporation actually plays out, including unresolved theoretical puzzles like the so-called black hole information paradox, concerning whether information about what fell into a black hole is truly lost forever or somehow preserved and eventually released, remains an active area of research. At the frontier of fundamental physics, the information paradox deserves a brief explanation of its own, because it illustrates just how unsettled the deepest implications of black hole physics remain, even decades after Hawking's original discovery. Quantum mechanics, one of the two pillars of modern physics, includes a principle holding that information is never truly destroyed. That in principle, given complete enough knowledge of a system's final state, you could always reconstruct everything about how it got there. But if a black hole evaporates completely through Hawking radiation, and that radiation turns out to be purely random, carrying no detailed information about whatever fell into the black hole over its lifetime, then information genuinely would have been destroyed in apparent violation of this core quantum principle. Resolving this tension, figuring out whether and how information about a black hole's contents might be subtly encoded within its outgoing Hawking radiation, despite appearing random at first analysis, has occupied some of the most capable theoretical physicists alive for several decades, including work using mathematical tools borrowed from string theory and quantum information theory. Meaningful theoretical progress has been made in recent years, though a fully satisfying, broadly agreed upon resolution remains, as of this documentary's writing, still a work in progress. It is also worth noting that Hawking himself, characteristically, revised his own thinking on related questions multiple times across his career, a reminder that even foundational figures in this field continued refining their understanding of black hole physics throughout their working lives. Rather than arriving at a single, final answer early on and treating the matter as settled, what the theory does suggest, with reasonable confidence, is the broad shape of the ending. Every black hole, no matter how massive, will eventually evaporate completely, given sufficient time, through the slow, patient leakage of Hawking radiation. The final moments of that evaporation, for any given black hole, are expected to become increasingly rapid and energetic as the black hole shrinks, a process sometimes described as ending in a faint, final flash of energy, releasing whatever remains of the black hole's mass in one last burst, before the black hole vanishes entirely, leaving behind nothing but the radiation it emitted across its entire, almost unimaginably long lifetime. This means that even the black holes that, for a time, will represent the last significant structures in the universe, including, eventually, the central black hole anchoring our own galaxy's distant future, are not truly permanent. They are so simply extraordinarily patient. And once even they are gone, what remains is a universe with no black holes, no stars, no stellar remnants, and, depending on which theoretical predictions about the deepest future eventually prove correct, perhaps not even ordinary matter, as we currently understand it. We have now reached the genuine frontier of established physics. The point in this story where confident, well-tested prediction gives way to careful, well-reasoned speculation built on theories that remain unconfirmed, even though they follow logically from some of our best current understanding of particle physics. The question at the center of this frontier is deceptively simple. Is ordinary matter, specifically the protons that make up the nuclei of every atom, including every atom in your body, every planet, and every star that has ever existed, permanently stable? Or will protons themselves eventually decay into other particles, given enough time? In the everyday physics we can test directly, protons appear to be perfectly stable. No experiment has ever directly observed a proton decaying. Several theoretical frameworks that attempt to unify the fundamental forces of physics, broadly called grand unified theories, which attempt to describe the strong, weak, and electromagnetic forces as different expressions of a single, more fundamental force at extremely high energies, predict that protons should, in fact, decay, though only after an extraordinarily long average lifetime. Experimental searches for proton decay have been conducted for decades, using enormous underground detectors filled with thousands of tons of water or other material, specifically designed to catch the extremely rare signature of a proton decaying, if it happens at all. So far, no confirmed proton decay event has ever been detected, which has allowed physicists to place a lower limit on the proton's lifetime, if it decays at all, of at least 10 to the 34th power years, based on results from experiments like Super Kamiokande in Japan. Meaning that if protons do decay, the average proton must survive, on average, for at least that staggeringly long span of time before doing so. Super Kamiokande is itself a remarkable achievement of experimental physics. A cylindrical stainless steel tank, roughly 40 meters in diameter and 40 meters tall, built in a zinc mine more than a kilometer underground to shield it from cosmic ray backgrounds, and filled with around 50,000 tons of extremely pure water. Its walls are lined with roughly 11,000 light-detecting sensors called photomultiplier tubes, each one watching the water for the faint flash of Cherenkov radiation, the blue glow produced when a charged particle travels through water, faster than light travels through that medium. That would indicate a proton decaying somewhere inside the tank. The underground location matters because cosmic rays constantly strike the atmosphere and produce showers of particles that would otherwise mimic the signature of proton decay, making the experiment impossible to conduct near the surface, despite decades of watching enormous amounts of matter. With exceptional precision and sensitivity, Super Kamiokande has never detected a confirmed proton decay event, an outcome that has forced theorists to revise or rule out several of the simpler grand unified theory models that predicted proton lifetimes short enough to have been detected by now. The simplest version of the SU-5 Grand unified theory, for instance, predicted proton lifetimes roughly 2 orders of magnitude shorter than Super Kamiokandé's current lower limits, and has been essentially ruled out by the experiment's non-detection results. A successor experiment called Hyper Kamiokande, essentially a much larger version of the same concept with roughly 8 times the water volume of Super Kamiokande, is currently under construction in Japan, with operations expected to begin in the coming years. Hyper Kamiokande will be sensitive to proton lifetimes up to roughly 10 to the 35th power years in some decay channels, extending the experimental reach significantly, and either detecting proton decay if it occurs within that range, or further narrowing the theoretical space within which grand unified theories can propose it might happen. Either outcome would represent significant progress in fundamental physics. It is important to be precise about what this means scientifically. This is not a confirmed phenomenon. It remains entirely possible that protons are permanently stable, and that no grand unified theory predicting their decay is correct. The continued failure to detect proton decay, despite increasingly sensitive experiments, is consistent with either possibility. Protons could be stable, or they could simply have a lifetime even longer than current experiments are capable of probing. If protons do decay, however, the consequence for the deep future of the universe is profound. It would mean that ordinary matter itself is not permanent. Every atom, every isolated particle drifting through the emptiness left behind after the black hole era would eventually break down into lighter particles, generally predicted to include positrons and photons, depending on the specific decay pathway involved. Over a timescale that current limits push out to at least 10 to the 34th power years, and quite possibly significantly longer. Should this prediction prove correct, the final stage of cosmic history, sometimes referred to by cosmologists as the Dark Era, would be a universe containing no black holes, all having evaporated through Hawking radiation, no atoms, all having decayed through proton decay or similar processes, and instead an extraordinarily thin, cold haze of fundamental particles, photons, neutrinos, electrons, and positrons, drifting through a universe that has, by then, expanded to a scale that makes even the distances discussed earlier in this documentary look intimate by comparison. This documentary, in good conscience, must be honest about exactly how speculative this particular chapter of the story is. Unlike the accelerating expansion of the universe, confirmed by multiple independent lines of strong observational evidence, or the basic physics of stellar evolution, confirmed by literally millions of observed stars across every stage of their lives, proton decay remains a theoretical prediction without direct experimental confirmation. It might be correct, it might not be. What can be said with confidence is that current physics provides no mechanism by which ordinary matter could survive forever in a perfectly unchanged state, given a sufficiently long enough span of time, whether through proton decay specifically, or through some other, currently unknown process operating on similarly vast timescales. There is one further possibility worth addressing honestly, precisely because it occupies a strange and uncomfortable position at the intersection of established physics and genuine uncertainty. The theoretical possibility of vacuum decay, sometimes discussed under the more dramatic label of a false vacuum collapse. The underlying physics concept is genuinely subtle, but it can be summarized, without too much distortion, as follows. The universe we currently inhabit may exist in what physicists call a false vacuum state, a configuration of fundamental fields, including the famous Higgs field, discovered at the Large Hadron Collider in 2012, that is stable enough to persist for extraordinarily long periods, but which may not represent the absolute lowest energy, most stable configuration that is theoretically possible. If a lower energy true vacuum state exists, quantum mechanics allows for the theoretical possibility that a small region of the universe could spontaneously transition into that lower energy state through a process called quantum tunneling. If such a transition occurred, the consequences would be dramatic and, from the perspective of any observer in the affected region, essentially instantaneous and absolute. A bubble of the new, lower energy vacuum state would expand outward at very close to the speed of light. And within that expanding bubble, the fundamental physical constants and properties of particle physics would be different from those in the universe we currently know. Different enough that atoms, and indeed any structure remotely resembling matter as we understand it, would likely be unable to exist in their current form. It is worth emphasizing several important caveats before this idea creates any undue alarm. First, this remains a theoretical possibility derived from extrapolating measured particle physics properties, particularly the precise mass of the Higgs boson and the top quark, into regimes of energy and time far beyond anything that has been or could currently be directly tested. Second, even within models that suggest our universe might exist in a false vacuum state, the predicted timescale before such a transition would be expected to occur, if it occurs at all, is calculated to be vastly longer than the current age of the universe. Often cited in scientific literature as comparable to, or longer than, many of the other extraordinarily long timescales already discussed in this documentary, rather than anything remotely imminent. Third, and most importantly, this remains a genuinely unresolved area of theoretical physics. Some calculations suggest our universe's vacuum state may actually be stable or only metastable in a way that makes any transition so staggeringly unlikely as to be functionally irrelevant, while other calculations leave the question more open. The reason this documentary includes vacuum decay at all, despite its speculative nature, is not to manufacture drama, but because intellectual honesty about the deep future requires acknowledging that our current physics does not yet provide a fully certain, complete picture of how or whether the story of the universe definitively ends. Most cosmologists consider the slow, gradual processes described in earlier chapters: stellar death, black hole evaporation, and possibly proton decay, to represent the most likely path the universe's future actually follows. Vacuum decay remains a theoretically possible, but highly uncertain and almost certainly far more distant alternative. What unites every scenario discussed in these recent chapters, certain and speculative alike, is a single consistent theme. Every currently known process points toward a universe that becomes progressively simpler, emptier, and quieter over time, with no known physical mechanism that would reverse this trend or restore the rich, structured, star-filled universe we currently observe. If we follow every process discussed so far to its logical conclusion, galaxies receding beyond detectability, stars exhausting their fuel, stellar remnants cooling into darkness, black holes slowly evaporating through Hawking radiation, and possibly even protons themselves eventually decaying. We arrive at a final theoretical state that physicists describe using a concept central to thermodynamics: maximum entropy, sometimes popularly referred to as the heat death of the universe. Entropy, in the relevant physical sense, is a measure of disorder, or more precisely, a measure of how evenly energy is distributed throughout a system. A campfire represents low entropy relative to its surroundings, a concentrated, organized source of heat and light, distinct from the cooler air around it. Given enough time, that heat inevitably spreads out, the fire dies down, and the temperature difference between the fire and its surroundings disappears. At which point, no further useful work can be extracted from the system, even though the total amount of energy present has not changed. This is the essence of the second law of thermodynamics. In any isolated system, entropy tends to increase over time, eventually reaching a maximum at which all temperature differences have been smoothed away, and the system reaches a state called thermodynamic equilibrium. The entire universe, treated as a single isolated system, appears to be following the same fundamental pattern, just on a scale almost beyond comprehension. Stars represent localized, temporary pockets of low entropy, created out of the relatively higher entropy state of diffuse interstellar gas. Through the process of gravitational collapse, and stars spend that low entropy state by emitting useful, organized light, which is what makes possible everything from photosynthesis on Earth to the very visibility of the night sky. We began this documentary discussing: once every star has exhausted its fuel, once every remnant has cooled, once every black hole has evaporated, and once whatever happens to ordinary matter on the longest timescales has run its course, the universe would settle into a final state of thermodynamic equilibrium, an almost perfectly uniform distribution of extremely low energy particles and radiation spread across an unimaginably vast and still expanding volume of space, with no remaining temperature differences, no remaining concentrated energy sources, and therefore no possibility of any further organized process, structure, or, as far as current physics can determine, any form of activity that could meaningfully be called events occurring at all. This is the theoretical endpoint implied by current cosmological models, assuming dark energy continues behaving as a constant and no currently unknown physics intervenes. Not a violent ending, not a dramatic collapse, but an extraordinarily long, gradual settling into uniform, featureless equilibrium. A universe that has, in the most literal thermodynamic sense, run out of differences capable of driving any further process forward. There is one further wrinkle in the heat death picture that theoretical physicists have noted, and which is worth acknowledging even if its ultimate relevance to the far future remains unclear. Quantum mechanics does not actually permit a system to settle into a perfectly static state, even in principle. The Heisenberg uncertainty principle, one of the foundational results of quantum mechanics, places a fundamental limit on how precisely certain pairs of physical properties, position and momentum, for instance, or energy and time, can be simultaneously known and simultaneously fixed, at the extreme limits implied by a universe approaching thermodynamic equilibrium. These quantum fluctuations mean that the system is never truly perfectly still. There are always small, random fluctuations in energy and particle configuration occurring at the quantum scale, even in the deepest possible equilibrium state. Some theoretical physicists have noted that Given a truly infinite span of time, these quantum fluctuations could, in principle, occasionally produce extremely improbable, but not physically impossible arrangements of matter and energy. A spontaneous, statistical fluctuation resulting in some organized structure within the otherwise featureless equilibrium of the far future. The most famous version of this idea, sometimes called the Boltzmann brane scenario, after the 19th century physicist Ludwig Boltzmann, who explored related ideas about statistical fluctuations in thermodynamic systems, proposes that a sufficiently long-lived universe in equilibrium might very occasionally, by pure statistical chance, produce a brief, localized pocket of low entropy. Even in the most extreme version of the argument, a self-aware observer existing momentarily before dissolving back into equilibrium. Most physicists treat this kind of scenario as more of a theoretical curiosity and philosophical puzzle than a serious prediction about what the far future will actually contain, in part because the timescales required for such fluctuations to become non-negligible in probability are vastly, almost uncomfortably longer than even the already staggering timescales discussed throughout this documentary. But its existence as a theoretical possibility serves as a useful reminder that even the concept of a completely finished universe, in the absolute sense that might first come to mind when imagining thermodynamic equilibrium, is subtler than it initially appears when examined through the lens of the quantum mechanical physics that governs all matter and energy at their most fundamental level. It is worth being clear about something the heat-death scenario does not imply. Despite occasional popular misconceptions, it does not mean the universe stops existing, or that space and whatever sparse remaining particles it contains simply vanish. The universe, under this model, continues to exist indefinitely, continuing to expand forever, just in a state with no structure, no organized energy, and, crucially, apparently no capacity to support anything resembling complexity, change, or, as far as we currently understand the physics involved, any process that could be called happening in any meaningful sense. This is, by most standard accounts within current cosmology, the most likely ultimate fate of the universe, contingent on the continued, unchanging behavior of dark energy that we discussed at length in Part 1. It is also, deliberately, where we will pause before turning to something more personal, not what the universe's final mathematical state will be, but what it would actually mean and what it would actually feel like for any observer fortunate, or perhaps unfortunate, enough to exist somewhere along the way. Before continuing further into the personal, reflective territory ahead, it is worth taking a brief detour to acknowledge something that makes the heat-death scenario more meaningful rather than less. It is not the only ending cosmologists have seriously considered. For much of the 20th century, several competing pictures of the universe's ultimate fate were taken just as seriously, and understanding why they were eventually set aside helps explain why the picture presented in this documentary carries the confidence that it does. The first major alternative taken seriously for decades before the 1998 discovery of accelerating expansion was the so-called Big Crunch scenario. Under this model, if the universe contained enough total matter and energy, gravity would eventually overcome the outward momentum of cosmic expansion, gradually slowing the expansion, bringing it to a halt, and then reversing it entirely. In this picture, the universe would begin contracting. Galaxies would begin approaching, rather than receding from each other, and the entire cosmos would eventually collapse back down into an extremely hot, extremely dense state. In some versions of the model, potentially triggering a new Big Bang in an endlessly repeating cycle, sometimes called the oscillating universe model. This scenario was a perfectly reasonable possibility based on the data available before 1998. The deciding factor was always going to be the total amount of matter and energy in the universe, compared against a specific theoretical threshold, called the critical density. If the universe's actual density exceeded that threshold, gravity would eventually win, and a big crunch would follow. If density fell below that threshold, expansion would continue forever, though still gradually slowing under gravity's influence, approaching but never quite reaching a complete halt. The 1998 supernova observations settled this question, but not in the way either possibility had anticipated. Rather than confirming a universe destined to recollapse, or even a universe simply coasting toward ever slower eternal expansion, the data revealed that expansion is accelerating, a result that neither the Big Crunch model nor the simple coasting forever model had predicted, and one that required introducing the concept of dark energy to explain at all. The Big Crunch, while not entirely ruled out under every conceivable theoretical model, has been set aside by the overwhelming majority of cosmologists as inconsistent with the observed acceleration, unless dark energy itself were to undergo some dramatic and currently unsupported change in behavior. A second alternative scenario, taken seriously specifically because of how poorly understood dark energy remains, is sometimes called the Big Rip. This model proposes that dark energy's strength might not remain constant, as assumed throughout most of this documentary, but might instead continue increasing over time. A property sometimes associated with a hypothetical form of dark energy called phantom energy. If dark energy's strength increased without limit, the rate of cosmic expansion would not merely continue accelerating gently, as in the standard picture, but would accelerate so dramatically that, at some finite point in the future, the expansion would become strong enough to tear apart not just galaxies and stars, but planets, and eventually even atoms themselves, ripping the fundamental structure of matter apart in a finite, calculable amount of time, rather than the gradual, asymptotic fade described throughout the rest of this documentary. Current observational data does not support the Big Rip scenario. Measurements of dark energy's behavior remain consistent with a constant value, rather than the ever-increasing strength a Big Rip would require. And most cosmologists consider it a less likely outcome than the heat-death scenario described in the previous chapter. But it has not been entirely ruled out by current data, which is precise enough to constrain dark energy's behavior, but not yet precise enough to eliminate every theoretically conceivable alternative. A third scenario worth mentioning briefly, sometimes called the Big Bounce, proposes that even if the universe does eventually undergo something resembling gravitational collapse, that collapse might not end in the kind of singularity classical Big Crunch models predicted, but might instead bounce into a new phase of expansion governed by quantum gravitational effects, not yet fully understood or experimentally confirmed. This remains highly speculative, residing more within theoretical physics research than established cosmological prediction, and is generally considered less observationally supported than the other scenarios discussed here. The reason this brief survey matters is not to introduce doubt into the central narrative of this documentary, but to provide honest context for just how carefully the currently favored picture, gradual, accelerating expansion, leading towards isolated galactic islands and eventual heat death, has actually been tested against serious alternatives. This is not the only story cosmologists ever considered. It is the story that survived rigorous comparison against multiple competing possibilities, repeatedly confirmed by independent lines of observational evidence, while the alternatives were gradually set aside, not through preference or convenience, but because the data simply did not support them as well. This is, in its own way, exactly what good science is supposed to look like. Not a single confident narrative asserted from the outset, but several serious competing possibilities tested rigorously against accumulating evidence, with the best supported option emerging gradually and remaining open to revision should sufficiently strong new evidence ever require it. Let us return for a moment to a place introduced in Part 1. The future merged galaxy we called Milkomeda, formed from the union of the Milky Way and Andromeda, roughly 4 to 5 billion years from now, eventually absorbing the remaining members of our local group over a longer span extending tens of billions of years further still. Imagine, as a thought experiment grounded in everything we have established so far, a hypothetical observer. Biological or artificial, it does not particularly matter for the purposes of this exercise, existing somewhere within that galaxy, at some point roughly 1 trillion years from now, well into the era when every other galaxy has receded beyond detectability. But before the long, slow fade of Milkomeda's own stars has progressed very far, what would that observer's night sky actually contain? Looking inward, toward the body of their own galaxy, the sky would still be remarkably rich. Milkomeda, even 1 trillion years into its existence, would still contain enormous numbers of slow-burning red dwarf stars, the patient survivors discussed earlier in this documentary, many of them not even halfway through their multi-trillion-year lifespans. The observer's sky, in the direction of their own galactic disk, or the smoother elliptical structure that the merger is expected to produce, would likely appear dense with faint, reddish points of light, dimmer overall than our current sky, since the brightest, bluest stars would long since have died, but still unmistakably full of structure, still recognizably a galaxy. Looking outward, away from their own galaxy, into what we currently understand as intergalactic space, the observer would see nothing at all, not faint smudges requiring careful telescopic observation. As distant galaxies sometimes appear in our own sky today, genuinely, comprehensively nothing, no detectable light of any kind, from any instrument, regardless of sensitivity, because every other galaxy that ever existed would by then have receded beyond the cosmological event horizon we discussed in Part 1, their light forever, unable to complete the journey to this observer's location. If this observer had access to deep historical records, astronomical data passed down or preserved from an earlier era, perhaps even records originating from our own uncurrent civilization, preserved across an extraordinary span of time, they could in principle learn that other galaxies once existed and reconstruct mathematically why those galaxies are no longer visible. But without such records, relying only on direct observation, this observer would have absolutely no way of discovering that their galaxy was ever anything other than a solitary structure, alone in an empty universe. There would be no observational evidence whatsoever pointing toward the existence of other galaxies, because every photon capable of providing that evidence would by then be permanently unreachable. This is not merely a striking thought experiment invented for this documentary. It echoes a serious point raised within the published cosmology literature itself. In research examining how the accelerating expansion of the universe will progressively limit what future observers can learn about cosmic history through direct observation alone. Researchers studying this question have noted that a civilization arising late enough in cosmic history, once galaxies beyond the local group have receded beyond detectability, and once the cosmic microwave background itself has redshifted into undetectability, would lack not just the data, but potentially even the theoretical motivation to ever propose something like the Big Bang model in the first place, simply because the observational evidence that led human scientists to that conclusion would no longer exist to be observed. It is worth dwelling on the layered irony contained in that scenario. The very tools that allowed humanity to reconstruct the universe's history, the redshift of distant galaxies, the afterglow of the cosmic microwave background, the relative abundance of light elements like hydrogen and helium forged in the universe's first few minutes, exist as observable evidence today specifically because we happen to occupy a sufficiently early point in cosmic history, a civilization arising 1 trillion years from now, no less intelligent, no less capable of careful observation and rigorous reasoning, might nonetheless reach a confidently incorrect conclusion that their galaxy has always existed alone, in a universe that has always looked essentially as it does at the moment of their observation, simply because every piece of evidence pointing toward a different, richer cosmic history would already be permanently beyond their reach. This raises an uncomfortable but genuinely interesting question about the limits of empirical knowledge in any universe governed by an accelerating expansion. How much of what we currently believe about cosmic history rests on a kind of fortunate timing, a window of observational opportunity that simply happened to remain open long enough for intelligent observers to notice it before it closed? It is impossible to rule out, even in principle, that some genuinely important features of the universe's structure or history have already receded beyond detectability before any observer anywhere had the chance to notice them. A sobering thought, though one that does not undermine the reliability of what we can currently observe and test, so much as it highlights the fact that what we currently observe and test may represent only a portion, not the entirety, of everything that has ever been true about the universe's past. This thought experiment captures something genuinely profound about the structure of cosmological knowledge itself. It suggests that the richly populated universe we currently observe, a universe we can study, map, and reason about, specifically because we happen to exist during a relatively early, relatively crowded period of cosmic history, represents a genuinely privileged epistemic position, one that will not be available to observers existing at sufficiently later points in cosmic time, no matter how scientifically sophisticated those future observers might otherwise be. There is a particular phrase sometimes used by cosmologists discussing this scenario. We exist during the only period in the universe's history when its large-scale structure and history are actually knowable through direct observation. Earlier than this, the universe was too young, too dark, and too undeveloped, lacking the stars and galaxies needed to provide any meaningful information. Later than this, much later, but inevitably, the universe will have receded into causally disconnected, isolated patches, each one unable to observe enough of the wider cosmos to reconstruct its history through observation alone. We are not at the universe's beginning. We are nowhere near its end, but in a very specific and meaningful sense, we may be living through something like the universe's only window of cosmological visibility. A stretch of time, finite on both ends, during which the structure, history, and likely fate of the universe can actually be studied and understood by anyone fortunate enough to be looking. It would be reasonable, at this point in the documentary, to ask a very practical question. Why does any of this matter? Why should anyone today, living an ordinary human life on an ordinary rocky planet, orbiting an ordinary star, care about events that will not occur for trillions, or hundreds of trillions, or unimaginably more years into the future? Events that no human being, and quite possibly no descendant of humanity in any recognizable form, will ever witness. There are several honest answers to that question, and they are worth taking seriously rather than treating as an afterthought. The first answer is simply that understanding the universe's fate is, in a very direct sense, the natural extension of the same curiosity that drove the earliest astronomers to track the movements of planets, that drove Hubble to measure the distances and velocities of distant galaxies, and that drives every scientist today, studying the cosmic microwave background or distant supernovae. We are, as a species, characterized by an apparently deep-seated desire to understand the larger context we exist within. Not because that understanding offers any immediate practical benefit, but because the act of understanding appears to be valuable in itself, a basic expression of what it means to be a curious, conscious species capable of asking these questions at all. The second answer involves perspective, a theme we touched on earlier in this documentary, but which deserves to be revisited directly here. Learning that the night sky we currently observe represents a temporary, privileged window, rich with visible galaxies, precisely because we happen to exist during a relatively early, relatively crowded period of cosmic history, changes how that sky might be experienced. It transforms an ordinary clear night into something closer to a brief, specific, and genuinely fortunate vantage point. A view that earlier eras of the universe could not have offered because the structure to be seen had not yet formed, and that vastly later eras will not be able to offer either, because that same structure will have receded permanently out of reach. The third answer is more philosophical and worth stating carefully rather than dramatically. The process is described throughout this documentary. Galaxies receding beyond a horizon, stars exhausting their fuel, black holes slowly evaporating, matter possibly decaying, are not processes that threaten us or anyone currently alive in any meaningful or immediate sense. They unfold across timescales so vast that they have essentially no bearing on any decision a person might make today, any more than the eventual heat death of a campfire bears, on whether you should add another log to it right now. What they offer instead is something closer to a kind of cosmic self-awareness, an understanding of where, in the very long arc of cosmic history, our particular moment sits and what that moment actually looks like when measured against the full scope of what is theoretically knowable about the universe's past and future alike. There is a fourth answer, perhaps less often articulated, but worth including here, which concerns what the study of cosmic deep time does for science itself, rather than for any individual who happens to learn about it. The effort to project the universe's future, billions and trillions of years forward, has repeatedly forced physicists and cosmologists to sharpen and test their theoretical tools in ways that have indirect but genuine practical consequences. Hawking radiation, for instance, emerged from an attempt to understand what happens to black holes on extremely long timescales. And in developing that theory, Hawking and others, working alongside him, produced insights about the relationship between quantum mechanics and gravity that remain some of the most significant theoretical advances of the past 50 years, regardless of whether Hawking radiation is ever confirmed through direct observation. The study of dark energy's effect on cosmic expansion has driven the development of new statistical and observational techniques, now applied across every area of precision astronomy. The mathematical tools used to model the very early universe and its evolution connect directly to particle physics experiments conducted at accelerators, like the Large Hadron Collider, where energies high enough to approximate conditions in the universe's first fractions of a second are routinely achieved. In this sense, asking questions about the universe's ultimate fate is not merely an exercise in intellectual indulgence, however valuable indulgence of genuine curiosity might be on its own terms. It is an engine for theoretical and observational progress that has historically produced results reaching well beyond the original question in directions that could not have been anticipated in advance, and that continue to do so. None of this diminishes the significance of the present moment. If anything, understanding how rare and temporary the current cosmic conditions actually are. A universe still young enough, still structured enough, still bright enough to be observed and understood in this kind of detail, adds a particular weight to the fact that we exist now during precisely the window when this kind of understanding is even possible to achieve. Before drawing this documentary to its conclusion, it is worth returning, deliberately and directly, to the genuine uncertainties embedded throughout everything we have described, because intellectual honesty about those uncertainties is just as important as the confident parts of the story. The most significant uncertainty concerns dark energy itself, the mysterious form of energy responsible for the accelerating expansion that underlies almost every prediction in this documentary. Current data is consistent with dark energy behaving as a true cosmological constant, fixed in strength across cosmic time, which is the assumption underlying the entire timeline we have walked through. But current data does not yet rule out the possibility that dark energy's strength could change over time. And several large-scale observational projects currently underway or recently completed are specifically designed to push that uncertainty much lower. The Dark Energy Spectroscopic Instrument, known as DESI, located at the Kitt Peak National Observatory in Arizona, has been conducting one of the largest ever surveys of galaxies and quasars using the precise measurement of their distances and positions across billions of light years to map how the universe's expansion rate has varied across cosmic history. Early results, published in 2024, from DESI's first year of data, attracted significant attention within the cosmological community, hinting at possible deviations from a perfectly constant dark energy value. Though as of this documentary's writing, those hints remained at a statistical level, where the scientific community rightly urges caution rather than firm conclusion, since the history of cosmology contains many examples of preliminary results that were subsequently revised as more data accumulated. Separately, the European Space Agency's Euclid mission, launched in 2023, is designed to survey billions of galaxies across more than a third of the sky, using two independent methods: weak gravitational lensing, which maps the distribution of matter by measuring how it bends light from background galaxies, and galaxy clustering statistics, to produce some of the most precise measurements of dark energy's behavior across cosmic time yet attempted. Euclid is expected to release progressively larger and more precise datasets over the coming years. The Vera C. Rubin Observatory in Chile, scheduled to begin its legacy survey of space and time in the coming years, will add yet another independent line of evidence, using a 10-year time domain survey of the southern sky to track supernovae and large-scale structure with unprecedented statistical power. Together, these and other upcoming facilities represent the best near-term hope for determining whether dark energy is genuinely constant or whether it contains some subtle but measurable variation over cosmic time. And the answer, when it becomes available with sufficient statistical confidence, will directly refine the timeline of every stage of cosmic evolutions described in this documentary. What is certain, regardless of which specific value these surveys eventually pin down for dark energy's behavior, is that our current picture of the universe's long-term fate is robust enough in its broad outlines that no plausible measurement result would change the fundamental story. A universe expanding forever, losing galaxies to the horizon one by one, and gradually trending toward a quieter, emptier, simpler state over timescales that dwarf all of recorded human history combined. Should dark energy's strength change significantly over time, weakening, for instance, or even eventually reversing, the long-term fate of the universe could look meaningfully different from the picture presented in this documentary. A weakening dark energy could, in principle, allow gravity to eventually reassert itself on scales where it currently appears to be losing the contest, potentially altering or even preventing some of the long-term isolation and separations described throughout this story. A reversal of dark energy's sign, while considered less likely by most current theoretical and observational work, has been proposed in some theoretical models, and would imply an even more dramatically different future, potentially involving a return to overall contraction rather than eternal expansion. A second significant uncertainty concerns the more speculative physics discussed in the later chapters of this documentary. Proton decay and vacuum decay, specifically. As emphasized at the time, these remain theoretical predictions without direct experimental confirmation, motivated by reasonable extensions of well-tested physics into untested regimes, but not yet verified phenomena in the way that stellar evolution, galactic structure, or even the basic fact of accelerating expansion have been verified through extensive, repeated, independent observation. A third, More subtle uncertainty involves the limits of extrapolating any physical theory across timescales as extreme as those discussed in this documentary's later chapters. Periods measured in numbers like 10 to the 40th, 10 to the 67th, or 10 to the 100th power years. Physics has never been tested, even indirectly, across timescales remotely approaching these figures. And it remains a reasonable, open question whether some entirely unknown physical process, undiscovered and unanticipated by anything in our current theoretical framework, might become relevant at some point along the way, altering the picture in ways we currently have no basis for predicting. This documentary has tried, throughout, to draw a clear and consistent distinction between what current science establishes with high confidence: the basic fact and rate of cosmic expansion, its acceleration, the eventual fate of galaxies beyond our cosmological horizon, the well-understood physics of stellar evolution and death, and what remains genuinely speculative, clearly flagged as such whenever it has appeared: black hole evaporation through Hawking radiation, which rests on solid theoretical grounds, but lacks direct observational confirmation; proton decay, a theoretically motivated but experimentally unconfirmed possibility; and vacuum decay, a theoretically conceivable but highly uncertain and likely extremely distant possibility. The willingness to hold these two categories, confident prediction and honest speculation, clearly apart, rather than blending them into a single, uniformly confident narrative, is itself part of what makes this kind of cosmology trustworthy. The universe's actual fate may turn out to match the picture described in this documentary closely, in which case everything described here will have been, in a sense, an accurate preview of a genuinely unwitnessable future, or new discoveries, perhaps arriving far sooner than any of the cosmic timescales discussed tonight, may reveal details that meaningfully revise parts of this picture, the same way the 1998 discovery of accelerating expansion meaningfully revised the picture that came before it. Either way, the proper response is not false certainty and not dismissive skepticism, but the same patient, evidence-based curiosity that produced this picture of the future in the first place. A willingness to follow the data wherever it leads, and to revise the story honestly whenever new evidence requires it. We end, as documentaries about the deep future often should, by returning to the much nearer and far more immediate present. Tonight, if you step outside under a sufficiently dark sky, you will see roughly the same view that humans have been seeing, with only gradual change, for the entire span of recorded history. A sky dotted with stars from our own galaxy, and, under the right conditions, a faint glimpse of Andromeda. The galaxy we now know is not merely a distant smudge of light, but our own galaxy's eventual companion, already falling toward us, already destined to merge with the Milky Way into a single structure within the next several billion years. There is a particular instrument worth pausing on because it represents our most ambitious current attempt to look as far back in time, and therefore as far back toward the universe's earliest chapters, as current technology permits. The James Webb Space Telescope, launched in December 2021 and now operating 1 million miles from Earth, at a point called Lagrange 2, where the gravitational influences of the Earth and Sun balance in a way that allows the telescope to maintain a stable position and keep its instruments shielded from solar heat. The James Webb Space Telescope observes primarily in infrared light, which makes it uniquely suited for detecting light from the universe's earliest galaxies. Objects so distant and so far back in cosmic time that their light has been redshifted from the ultraviolet and visible wavelengths at which it was originally emitted down into the infrared, the only wavelength range where Webb's instruments can catch it. In its first few years of operation, Webb has been revealing galaxies that existed when the universe was only a few 100 million years old, closer to the very beginning of the stelliferous era than anything previous telescopes could study in comparable detail. And some of those early results have surprised astronomers, revealing galaxies that appear larger and more structurally developed at earlier cosmic times than many theoretical models had predicted, requiring ongoing refinement of our understanding of how quickly galaxies assembled their mass. In the universe's earliest chapters, every image the James Webb Space Telescope produces is, in a sense, a direct demonstration of the temporary observational privilege described throughout this documentary. Webb is looking at light that departed its source over 13 billion years ago, from galaxies that existed when the universe was less than 5% of its current age. That light has been traveling through an expanding universe for almost the entirety of cosmic history, stretched and dimmed by the very expansion that this documentary has described, and it is arriving at our detectors right now, in this narrow window of cosmic time, because the universe is old enough to have produced complex, detectable structure, and young enough that the expansion has not yet pushed those distant sources permanently beyond our horizon. The contrast between what Webb currently sees, a rich, distant, ancient universe teeming with early galaxies, and what any instrument built 1 trillion years from now could possibly see. A universe with nothing visible beyond the boundary of one isolated merged galaxy captures, perhaps more vividly than any single number or equation, exactly what this documentary has been describing. An extraordinary finite window of cosmic observability that we are currently inside, and that will not be available at any other point in the universe's extremely long history. Everything else in that sky beyond our immediate galactic neighborhood, every other galaxy, every other supercluster, every other strand of the cosmic web exists, for now, within a universe still young and structured enough for that light to have completed its journey to us. We are observing it specifically because we happen to exist during the portion of cosmic history when that observation is still possible, after the universe became old enough and structured enough to contain galaxies worth observing, but long before the accelerating expansion driven by dark energy has had time to push the vast majority of those galaxies permanently beyond our reach. The night sky, understood this way, is not simply decorative and not simply a fixed backdrop against which human history happens to unfold. It is a temporary, genuinely privileged view into a universe still rich with visible structure, a view that did not exist for the first several 100 million years after the Big Bang, when no stars had yet formed, and a view that will not exist in anything like its current richness. For the overwhelming majority of the universe's future history, once dark energy has had sufficient time to do what current physics suggests it will inevitably do. This does not make the eventual fading of that sky a tragedy exactly, any more than the eventual ending of any individual day is a tragedy. It simply means that what we are currently witnessing, a universe still busy forming stars, still close enough together for distant galaxies to remain visible, still young enough that its full history can be reconstructed through careful observation, represents a finite, specific, and genuinely remarkable chapter within a much longer story, one whose beginning we are still relatively close to, and whose true ending, if it has one in any meaningful sense, lies so far beyond any timescale relevant to human concerns that the very concept of waiting for it loses most of its ordinary meaning. What remains, knowing all of this, is something closer to appreciation than anxiety. An understanding that the sky above us tonight, ordinary as it might seem on any given evening, is the product of a very specific, very temporary set of cosmic conditions. Conditions that took 13.8 billion years to produce, that we are fortunate enough to exist within, and that will not last forever. Not because anything is going wrong, but because the universe, true to the physics that built it, is simply continuing to do what it has been doing since its very first moment. Expanding, evolving, and slowly, patiently, becoming something different than it is right now. We began this documentary with a question that sounded almost like science fiction. What will the universe actually look like after every galaxy beyond our own has disappeared? We now have a genuine answer, built not on speculation alone, but on decades of careful observation and well-tested physics, layered together into a coherent picture of the deep future. Galaxies will not be destroyed. They will simply recede, slowly, then increasingly rapidly, then permanently beyond a horizon that grows to claim more of the universe with every passing eon, leaving behind isolated, gravitationally bound islands like our own future, Milkomeda, drifting through an emptiness too vast for any signal to ever cross again. Within those islands, stars will continue burning for spans of time that make the current age of the universe look like the very first moment of a much longer day. The smallest, most patient among them, lasting trillions of years, before finally exhausting their fuel and settling into cold, dark remnants. Black holes, the most durable structures the universe produces, will eventually claim much of the remaining mass within those isolated galaxies, before slowly, patiently evaporating themselves over timescales that stretch the meaning of patient, well past anything ordinary language was built to describe. And at the furthest edges of what current physics can responsibly predict, genuine open questions remain. Whether matter itself is permanent or subject to an extraordinarily slow decay, and whether the vacuum of space we currently inhabit represents the universe's final, stable state, or merely a long-lived, temporary configuration. These questions, unlike the earlier parts of this story, remain genuinely unresolved. Honest uncertainties at the boundary of what science can currently tell us, rather than confident predictions. What unites every stage of this journey, certain and speculative alike, is the same underlying truth we encountered near the very beginning. The rich, structured, star-filled universe we observe tonight is not a permanent feature of reality. It is a temporary, remarkable condition, made possible by a very specific moment in a very long cosmic story. A moment we happen to occupy, and a moment that will not return once it has passed, for any observer anywhere in the universe ever again. There is something worth sitting with in that realization, not with alarm, but with the kind of quiet attention that belongs to genuine perspective. Human beings have existed for roughly 300,000 years, during a universe that is 13.8 billion years old. during what we now understand to be the middle chapters of a story whose total length, if it has a length at all, likely exceeds any number with an ordinary name. We did not exist during the universe's earliest, darkest centuries. We will not exist during the long, cold trillions of years that lie ahead. We exist precisely here, precisely now, during a chapter defined by starlight, by visible structure, by a night sky rich enough to have launched 10,000 years of human curiosity about what lies beyond it. Every civilization that has ever looked up, from the earliest humans tracking the movements of stars across a dark prehistoric sky, to the astronomers who first understood that the smudges of light they could barely resolve through their first telescopes were entire other galaxies, to the scientists operating instruments like the James Webb Space Telescope today, has been doing so during this same window, this same era, this same remarkable and temporary condition of a universe still bright enough and young enough and close enough together to be genuinely, meaningfully visible. None of them could see the whole story. Neither can we. But we can see more of it than anyone could a century ago, and more of it, almost certainly, than anyone saw before telescopes existed at all. That gradual expansion of our view, from local star patterns to the solar system, to the galaxy, to the observable universe, to the deep future timeline described in this documentary, is itself one of the most extraordinary things our species has managed in its brief and improbable existence. The slow but unmistakable expansion of the window through which we see the universe we were born inside. What each of those generations of observers had in common, across every culture, every era, every level of technical sophistication, is something simpler than any particular theory or instrument: the willingness to look up and ask what they were seeing. That impulse, repeated across thousands of years, and eventually given increasingly powerful tools with which to pursue its answers, has produced the picture of the universe described in this documentary. It has revealed a cosmos approximately 13.8 billion years old, containing hundreds of billions of galaxies, governed by physical laws consistent enough across its entire observable extent that equations written on Earth correctly predict the behavior of matter and energy billions of light years away, and stretching forward in time through a future so vast that it renders the present moment, for all its felt urgency and weight, something almost impossibly brief by comparison. That knowledge, imperfect, incomplete, continuously revised, is among the most remarkable things living creatures, embedded inside a physical universe, have ever managed to produce about the nature of the place they inhabit. It is worth carrying that recognition forward, not as an abstraction, but as a specific and genuine appreciation for what the unassuming night sky above us tonight actually represents. There is a particular kind of wonder available only to a species capable of understanding this. Not wonder at any single object in the sky, however spectacular, but wonder at the entire unfolding story those objects are part of. A story stretching from a universe with no galaxies at all, through the relatively brief, brilliant window we currently inhabit, and onward into a future so vast, so strange, and so far beyond ordinary human timescales that even the boldest science fiction rarely attempts to describe it with the same patience that physics actually requires. We do not know with certainty exactly how this story ends. We may never know, but we know with remarkable confidence how it unfolds across at least the next 100 billion years, the next trillion years, and considerably further still. And that knowledge, however incomplete at its furthest edges, represents one of the genuine triumphs of human curiosity. The ability to look up at an ordinary night sky and reconstruct, through nothing but careful observation and patient reasoning, the entire arc of a story that began long before we existed, and that will continue, in one form or another, long after we are gone. The galaxies above you tonight are still there. For now, they are still visible, still reachable by the light they sent toward us long ago, still part of a universe rich enough and young enough to offer this particular view. That, perhaps, is the most fitting note to end on. Not the universe's eventual emptiness, vast and certain as that future is, but the specific, temporary, genuinely extraordinary fullness of the moment we are fortunate enough to be living in right now.